Okay, was sorry about the people online was muted, right? Okay, so so here I will just quickly show a figure that so it's very limited ocean in the interior ocean below the surface. To mention the ST is the most observed variable before satellite. And that's why it's quite important the data set for long term. I would say 100 years or 150 years climate reconstruction. And but we have there's quite a challenge as well to yeah, like I show a map. It's follow the ship's track, right? That's the average over 1955 until 2012. So you see most of measurements is along the track. Somewhere is very dense observation, somewhere is less. And also before that, so we use a different type of instrument to measure the temperature, sea surface temperature, like wooden bucket or carnava bucket, different bucket, you know. It's quite difficult to use directly the observation. They have a different representativity, different error. Okay, start, right? Difficult to use directly such kind of data. So in practice, we use kind of a 2D kind of graded data like ST analysis product. So I will, based on that, to reconstruct 3D or even 4D climate reconstruction. This one. So okay, isopycnal coordinate ocean model is kind of a Lagrangian model where the vertical is discretized by the water density, as I'm showing here. So with different layers instead of meters, 5 meters, 2 meters. Such kind of a model is has allowed very good conservation of water properties like heat and salt, which is kind of very good for climate studies. So we, based on that, we Norwegian, not only Nansen Center, but a lot of different institute, we developed a system called the Norwegian Earth System model, where the ocean micro is in such kind of model. And then we have we added data simulation ensemble common filter. So we developed the Norwegian climate prediction model, not for climate prediction, but also for climate reconstruction. And some previous papers showed not only Earth, but also other people showed that data simulation in isopycnal coordinate is efficient than in Z level, at least for such kind of a model. And we, in our previous study, we have we try to play with the layer thickness from one to another. It's also one important variable as well for such kind of model. And we play, because of course it's not Gaussian, it never becomes 0 or negative, right? So consider this issue. We have elevated somehow the bias introduced by SST assimilation, but still kind of a slow drift in the ocean interior remain. Here I showed kind of 2 examples. So like the area I show here is we call the subpolar dry region in the bit south of Greenland. So that's the average or Hofmöller plot for this region from surface to 5,000 meters. The top panel shows the simulation or with data simulation, of course. But for our system, another one, EnKF, kind of objective analysis, but we constantly they use the TS profiles inside. So there we believe a bit more in EnKF. So from that expect, so you can see in in surface more or less fine, but in the deep ocean, it's a lot of difference. And then, so if we want to predict, the pink lines here is the prediction from the red one, the reanalysis. So you can see the prediction, 10 years prediction of this area, the heat or the temperature over 2,000 meters. There's a kind of a fake or false warming signal comes up very quickly after initialization. So Petchek, they reported this mainly from the issue of initialization error in the subtropic heat content. So we have tried to use kind of a, how to say, localization, kind of ad hoc, as many are familiar with that. So it's the ad hoc technique to try to solve this issue, or to at least remove or reduce a bit the bias. So typically, because we have a very big system, but we use 30 members, localization is kind of very good tools to reduce, or at least reduce the sample noise that can be degrade the solution or the performance of the system. And very quickly show that, so when we use a tapering function, like even step function, 1 or 0, we taper our sample correlations, so you get the orange line, or more or less like that. Of course, we can use a more fancy function like a smoother or Gasparian-Cohn function. I will get a more smooth update or increment. But for our model, isopycnal coordinated model, because from one layer to another is less communication compared to Z-level models. So far we are not sure yet. So maybe, yeah. So which kind of model, which kind of type of function will be beneficial for our model, especially. And what we did, so we estimate different type of tapering function, step function or smooth function. So we run our model with 1 members because it's very expensive. So we, and for 115 years, and then we for each month, then we have a kind of, we consider that's our ensemble, a bit larger static ensemble. And then we perform kind of a bootstrap technique to sample 1,000 ensemble of the size of 30. 30 is our dynamic no CPM ensemble size. And then we estimate for each member, each ensemble, the correlations between ST, for example, and the temperature or salinity. In the coming slide, I will show only the correlation between ST and the temperature. And then I will quickly show for other variables as well. Just one slide. So here, that's the estimation from 1,000 correlation profiles at different locations. And the blue line is the average of correlations. We consider it's more accurate than just so random. And then the blue shading is the kind of uncertainties. Here I'm showing it from 5 to 95 percentile. And the dashed line is the vertical layers where below that it become no significant anymore. The left side is very easy. So if you go from up and down, then you will touch like 19, the layer 19. Below that, all is not significant. But some area like the right side, so you can be switched from positive to negative and then go to a positive significant again. It really depends on the ocean stratification. And so then, for example, if we want to use that kind of to define the step function 1 come to 0, so left side is just update 1 until 19, and then go below is 0. Okay, this meaning we opted only for until 19 layers. So if we take the both, so as I showed here, there are some location, there are many choices. You can choose up and down, the top and the bottom. So if you take the bottom, every location, you take bottom, top threshold layers, you get this kind of map for January, and the bottom is for July. Different month. There's some change from month to month, especially in the high latitude region, like Arctic region. And if you take the bottom threshold layer, so you want to have a maximum impact of our ST observation. So then you can get this map. Typically in the Ansel region, you see the water change, how to say, quite significantly, and then you will get this kind of a deep impact because of the ocean with stratification. And then we'll quickly talk about the smooth tapering function. So most time we suppose the filtered matrix, the P with hat equal to kind of a short product of a logulation and our original background covariance matrix. And based on the Minity et al. 2015 paper A, and then we can get the logulation Lij matrix is from this formula. It's a function of ensemble size n, and also the expected value of variance and covariance between I and J. And here I'm showing at different location. The blue line is the correlation. The red line is kind of a logulation estimated from Minity formula. So you can see it's kind of a follow the correlations shapes, but a bit higher value. And then I will talk about what I showed is the correlation between ST and the temperature. And we will, of course, we want to update the salinity as well, the layer thickness, and the UV is the velocity. And here I'm showing the map, a figure about the sample correlations between ST and the temperature, salinity, and the layer thickness. So you can see the blue and the red line are more or less identical below mixed layer. And for layer thickness is quite change a lot from layer to layer. So so far we do not have a better solution. We just perform our localization, vertical localization only for temperature and salinity. And I performed 2 experiments over 80 to 2010. So the free one is the historical simulation with 30 members. And then we pick up, we swap one member from member 1 from the free, and perturb its initial condition, and in 1960 at the truth, and then we generate the observation from the truth. Then we perform several experiments. One is reanalysis without vertical logulation, and then 3 with the logulation, different type function, like a step function with the top threshold layer, I call the minimum support, and another one is use the bottom threshold layer, we call the step function with a quite big maximum support, and then smooth function. Sorry, that is typo. It's a smooth tapering function. And then I use the matrix kind of a difference delta RMC or mean square squared skill score. Yeah. So here is the whole model over, over the whole ocean area. You can see with can you see the title? Yeah. Anyway, that's the MSS. From surface to 5 kilometer. The left side is for temperature, and the right side is for salinity. And you can see by assimilating sea surface temperature data, we have a slow, how to say, the drift in the around from 2 kilometers to 4 kilometers deep. And then with step function, with minimize very small spot, so you can reduce and or elevated somehow the bias over there. And if we use the support, larger support of a step function, so you see we almost everywhere is positive. Positive means improvement. And then it's with a smooth function, step function, temporary function, you can see it's a bit similar, but slightly, I mean, degradation compared to the step max for salinity. Then I'm showing the map for the difference delta RMSE between the reanalysis and the free run. So you can see this I think this one is how to see, maybe I don't know how to hiding this one, but this one is for the temperature and salinity over between, I think it was 1,000 to 2,000 meters, and you can see for there's some areas of degradation in the subtropical Atlantic region and also Pacific region, both for salinity and temperature. And when we use step functions like I'm showing here, you can see how to say we elevated somehow the bias. Typically, the step max work quite good for North Atlantic region where when I introduce my program. Then with a smoother, it's slightly worse, but still good compared to no log regression simulation. Then if we go down below 2,000 meters in the ocean, without vertical logration, you can see blue is the degradation by a simulation of ST, and then with this different type of step function, you don't have such problem. But of course, you see some areas in the South Ocean still blue, but we cannot expect vertical logration solve every problem, all problem. It's still a problem with, like from the model itself, right? Yeah, so take home message. So vertical logation in isopycnal, we have performed vertical logation in isopycnal coordinate ocean model for climate reconstruction. And we found vertical logation, at least, in our case, improved the performance of reanalysis. And we designed three type of schemes, two type of step function, one smooth tapering function, and the step function with a larger support overperforms the others. And the future perspectives. So we are trying to combine the vertical log elution with hybrid covariance. Hybrid covariance meaning dynamic ensemble 30 and with static ensemble members. So hope we can show next year. And then we can try to verify in a real framework. By assimilating the real data, or we can adapt to hydrographic profiles or observations as well. We can also assess the impact of vertical logation on kind of a climate prediction, try to improve the skill. And maybe, as I showed you, if you remember, so there's some location there from the significant correlation become insignificant and then go to negative uncorrelated. So could we use multi-step function? It's 1, 0. You just select, as I show here, you only consider the layers in which the correlation is significant. Ignore the various transition layers. And maybe apply to layer thickness and velocity UV. In that sense, so we need, probably we can decompose the velocity or the layer thickness into different mode, like bioclinic or biotropic mode, and only update the bioclinic mode. Yeah, I think I will stop here. Thank you very much for your attention.
Perfect timing. So we have 5 minutes for questions.
I have a question about bootstrapping. Were you saying that you select 13 Java members out of 1,000?
Yeah, so when I bootstrap repeat 1,000 times.
1,000 times.
Yeah, but the ensemble size is always 30.
Okay, in that case, it's even expensive. It's more expensive than you just use 1,000.
Yeah, because that we do only once. Then
you mean only once for bootstrapping?
I mean, so okay, when we estimate the step function or all the 3 functions is based on the kind of static ensemble member. So we run once one member for 300 years, then it's done. We based on all these 300 member year simulation to estimate the uncertainty of ensemble size of 30.
Yeah, thank you.
I don't see anyone.
Thanks, Ivo. Can you comment on how different members will have different physical heights in the isopixel coordinate? Will that
Different
change differently because the ensemble have different density in their columns, so the actual location of these vertical heights are different? Will that impact the?
So when we, the model state is in isopixel coordinate. We do not interpolate to Z level as I showed. Is less interesting. So when we cross members, they are in the same density instead of the same Z level coordinate.
Okay, so the second talk of this session is from Simone Spada, and he will talk about Gaussian high-order sampling hybrid filter for biogeomechanical data simulation.
To have a microphone.
Okay, test. Okay, so hi everyone. A little bit of overview of this presentation. So first, an introduction with the main points of novelty of this work. Then I will try to convince you that you are not totally wasting your time listening to me. And then I will test your resistance with some technical details. And if you survive, you will be rewarded with some nice results. Okay, so the Gaussian high order sampling hybrid filter, we call it GAUSH, is a novel ensemble filter developed at OGS. Main features are a new sampling method called the high order sampling for weighted ensembles. And this sampling method is used twice into the analysis step. And I will explain why. And the third main feature is a non-orthogonal model error projection into the ensemble subspace, but I won't talk about that here. So I will focus on the sampling. So let's start. And why we need an ensemble? Why we need the sampling? Well, because we usually start by from probability distribution function. Then we have a model operator. We want to evolve this probability distribution function, but evolving a PDF is hard. So we sample an ensemble from our initial PDF, and then we evolve that ensemble. Now the question is, it's true that the evolved ensemble is still representative of the PDF after evolution? Well, the answer sadly is no. So there are a few facts. If the model is linear, then the evolved ensemble is as good as the initial ensemble. Good here means that has the same statistical moments as the PDF. If the model instead is a second order polynomial, then we need to have same covariance and mean in the initial PDF and the initial ensemble in order to just have the same mean in the evoluted or forecast ensemble. And this is what is done usually in square root filters like SEK, ETKF, ETKF, etc., etc. But the model is usually more general than a second order polynomial, right? So an error term appears, and this error can be relevant. Okay, so how can we do better than this? Well, if we can, if we can take into account a second order polynomial by having an ensemble that that have same covariance and mean as the initial PDF, so the up to the second order moment, then can be proved that if we have an ensemble that match the initial PDF up to a higher order, up to order n, let's say, then we are exact up to a polynomial order of n. So this means that we are taking into account the first n terms of the Taylor expansion of the model. Okay, so this essentially means that if you have a higher order, then you are working with smaller errors. And this is true for the estimation of the covariance too, not only for the mean. So what we want is an ensemble matching higher moments, not only mean and covariance. Okay, let's make a small example. Just take Gaussian distribution as an example, and shady areas represent the probability. Okay, with the second order exact sampling, we just need 3 ensemble members in order to represent these 2D-dimensional Gaussian. With 4 ensemble members, we can achieve a third order sampling. So we have the same moment up to the third statistical moment. And you need 7 ensemble members, weighted actually ensemble members, in order to achieve the 5th order. Okay, so this seems everything simple and clear, but 2 problems arises. First, if we want to sample with an higher order, we see that we have to solve a nonlinear system, and solving nonlinear system is not easy. Second problem is that we need more ensemble members. Usually, in the second order sampling, we just need D+1 ensemble members, where D is the dimension. So in our previous example, we need 3 ensemble members in dimension 2. But if you want to have an higher order, then you need more ensemble members. This is a problem because evolving ensemble members is costly, computationally costly. We are usually the model operator is the most demanding part of the data simulation. Okay, so accordingly to Tron 1982, there's no problems, only solutions. So now we have 2 solutions. If you have a big nonlinear system that is hard to be solved and demanding, then let's just solve it once in a special case offline and find a way to use that solution every time. And then for the larger ensemble, it is a little bit more tricky. So first of all, use a weighted ensemble instead of just an ensemble. In this way, you reduce the number of ensemble members that you need. And then this is not sufficient. So we accept to lose a little bit of accuracy, but only where it is not so relevant. So now I'm going to explain a little bit these 2 solutions with a more details, a higher number of details. So we have to start from a little bit of history. The second order exact sampling is what is used usually in all the square root filters like SEIC and other filters. We start from a covariance P that is too big for being taken into account as it is. So we approximate it with a base L and a symmetric matrix A smaller than P. So the base L is the base of the sub-arrow subspace. And we are looking for X, that is the ensemble matrix, such that its covariance is the same as the approximation of P, so LALT. A second order solution is given by LS omega, where S is the square root of A, and omega is a random matrix that has 2 special properties. So have orthogonal columns and 0 mean. So omega is the true key of the sampling, of the second order sampling, because essentially omega is the columns of omega are a second order sampling of a standard Gaussian. So in this interpretation, LS is just a projection in the error subspace, and omega already contains the sampling in a standard situation. So instead of putting into omega the second order sampling, we can put inside omega a sampling of an higher order and just compute it once in a standard situation. So what happens is that we can factorize omega into 2 matrices, omega random and omega h. Omega h is fixed and requires the solution of the nonlinear system, but you can solve it just once. And then the omega random is just a random orthogonal matrix, which is easy to compute and can capture all the randomness of omega. So essentially, it is all the possible rotation and symmetry. And in this way, we have obtained, we have solved the problem of the nonlinear system. About the problem of the ensemble sites, let's go back to our ensemble, and we see that in two dimensions, just 3 ensemble members are needed for a second order sampling. And it is impossible to achieve the third order with less than 4 ensemble members. So this seems to be a no exit situation. But what if those 4 ensemble members came from a second order sampling in 3 dimensions instead of 2? So let's work in 3 dimensions instead of 2. Now, a second order sampling has 4 points. But if we look at this 4 points into 2 dimensions, then those 4 points become a sampling of an higher order. It's like playing with shadows. If you take a tetrahedron, you can put it in a way such that you project a perfect square as a shadow. Try it at home. Okay, so what's happening is that we can achieve a 5th order sampling for example, in 1 dimension, which is obtained by 3 weighted ensemble members, thinking of them as a projection of a 3rd order sampling in 2 dimensions with 4 ensemble members, which is a projection of a 2nd order sampling in 3 dimensions with 4 ensemble members. Yeah. Okay. So what I'm saying is that you can work up to the 2nd order into your whole error subspace, but in some directions, in those directions, you are achieving a higher order of approximation. So this means let's do principal component analysis and orient the system in such a way that in the most relevant component, in the most relevant directions, we are approximating well with a 5th order, for example. And in the less relevant component, we stay to the 2nd order. Okay, this is achieved into the Gauche filter by this E matrix, and that is inside the X. So X equal LS, that was our old base, and E is a change of base actually, and is obtained by an eigenvalue decomposition of SLT LS. And since it's an orthogonal matrix, then is not changing anything. I mean, the covariance is the same. Is just a change of base, and inside omega we put our solution. Now we cannot have an omega random and omega H mechanic as before, because here the direction is relevant. But in any case, trust me, you can take into account all the randomness inside omega in some technical way. So, okay, ensemble sites and error subspace now are the same as in square root filters. So we are not losing anything, but we are approximating better in the most relevant directions. Okay, so now we have this high order sampling method, and we can use it to better approximate the action of an operator. We have used it for the model operator, but we have the observation operator too. So why don't you use it into the observation operator too? Because the observation operator is used into the ensemble members in order to approximate the likelihood PDF that is used to obtain the assimilation. So usually we use the observation operator directly into our starting ensemble, right? But this is not a good way to do, because we have inflation or model error or anything else. It is needed in most of the cases, and inflation is going to change the forecast PDF. So our forecast ensemble is no more well representative of the forecast PDF. It does not even have the same covariance. And the observation operator is non-linear in most of the cases, at least in biogeochemistry, where we have log normal distributions, so logarithmic variables. So, okay, this means that it's better to resample twice. Okay, so a little experiment. In OGS, we focus usually into biogeochemistry, so it is an experiment into the biogeochemistry of the Mediterranean system. We used a biogeochemistry model coupled with a transport model, so BFM plus OGSTM. We used satellite chlorophyll as observation. So the setup is 1 year simulation, 1/4 degrees of horizontal resolution, 16 ensemble members. We checked the results with RMSD2 independent data, a total of 18 tests with different parameters. What we obtained is that the sampling order was not strongly effective on the assimilated variable, that's the chlorophyll, but in a non-assimilated variable, the nitrate, we have an improving up to 80%. These are the numbers actually. So why we didn't obtain a strongly effective effect on the chlorophyll, we don't know. Probably is because the variability of the chlorophyll is not lying in those directions that are taken into account by the PCA. Who knows? Or probably because second order is sufficient to work with chlorophyll. But what we can say is that with the nitrate, we have obtained very good results, or at least encouraging results. Okay, just a few remarks. The gauge filter has been implemented into the parallel framework developed by OGS inside the Seamless project. And a very important thing is that the computational cost of an assimilation experiment with the gauge filter is equivalent to other square root filters. So we raised the order of the sampling with no costs, so no downsides. Future developments, we are going to test gauge and SEIC in a full resolution model, and a manuscript is under submission. So mail me if you want to see the final version. And thank you.
Yeah, we have plenty of time for questions. Okay, no jokes this time.
Thank you for a very exciting talk. First, standard boring question, but important nevertheless. Did you test it on the toy example?
Yeah, and yeah, this is part of my PhD thesis. So we tested it in a toy example, and it was good. And we were interested in see how he behaves into a realistic model. So
the toy example is in the manuscript?
No, the toy example is not in the manuscript. This is a choice due to the fact that we are preparing a manuscript for the oceanographic people. So it will be probably in ocean modeling. And we think that they will be probably not interested into.
But I will. If you publish in another journal, perhaps. I mean, you have a new method, so then you should demonstrate the method before applying it to conflicts.
Yeah, you're right. We can. Well, actually, there's a second paper in preparation that is only from the mathematical point of view. So purely demonstration. But I think that it will need a little bit more of time to be published. So yeah.
And as I said, I found it very exciting. Unfortunately, I don't follow everything, so I'll just ask maybe one question. For example, so omega is always, we call it a rotation matrix, although it might be a reflection matrix as well. You said it represents the standard Gaussian sample, but I mean, how you generate it normally is you sample, say, a Gaussian, but any elliptical multivariate is okay, and then you take the SVD and just use the left singular.
Yeah. So I said Gaussian, standard Gaussian, just because it is easy to understand. But what I mean is that this is a sampling up to the second order if any PDF which have covariance, identity matrix has covariance, and zero mean. This is what the equation are saying. So omega times omega transpose is 1. This means that the covariance is the identity matrix, and omega times the vector of all ones means equals 0, means zero mean. So it is not only about Gaussians. Yes, any distribution that has this property. Yeah, I want to add that the Gaussian into the name of the filter. So it is a Gaussian high order sampling hybrid filter, but that Gaussian it is not something that refers to the probability distribution, but it refers to Gaussian Hermite quadrature, because it is based on that thing. So it can be suitable for any kind of probability distribution.
Do we still have time for one more question?
Yes, the question.
Only I can ask one.
So you say you have the same, basically same dimension as for the square filters.
Yeah. The same, sorry?
Yeah, the same complexity of the
Yeah, exactly.
So the question then is this a free lunch, or is there something else going on here? Makes it a bit more complicated.
Well, yeah, the point is that into the data simulation algorithm, the data simulation part, so where you solve the matrix products, then you have to do a little bit more of work, of computational work, but it is totally irrelevant with respect to the evolution of the ensemble. So you essentially won't note any difference using the sake or using the Gaussian.
I have one question. Sorry. I think you come up with second matrix because you want to match higher order moments.
Mm-hmm.
And you said that this higher order system is actually nonlinear, but you didn't show that.
Yeah.
In a way. I would be curious what this kind of equation could be, so that we need to solve this system.
The equations are moment matching equations. So if you have as incognitas your sampling, then you have to put the first, second, third moment of these ensemble members equal to the moments of your probability distribution. So it's just writing down equations about matching the moments. So it's quite complicated to see if you look at it into the screen, but it's nothing mysterious. It's just imposing that the moment from the ensemble is the same, and then solving to found the ensemble.
Okay, I got it. And I have two questions, Ivo and yeah, thanks for the very nice talk. I just wondering when sampling how preserve the dynamic consistency, or if there is something will break the dynamic consistency between different variable or between.
Yeah. I don't know if I know how to answer to this question. We saw that in the biogeochemical case, we had no problem into this sense, but I don't know if in a physical system there can be some kind of problem with preserving pressure or what else. But I think that is something that is the same as in other square root filters. So I don't know if I have answered.
Next question, I guess. Thank you. I enjoyed your talk. Really interesting. And in the examples, I guess you showed that it improves the analysis error in the mean. But I missed, do you have any intuition for why, if your ensemble sort of matches some higher moments before you do the analysis, why would you expect that to improve the accuracy of the mean after the analysis?
Yeah. This is exactly, well, this is a little theorem actually. So the point is that if you match up to if your ensemble matches the second statistical moment, so the covariance, then you are this can be proved mathematically. Then you are exact into the evolved mean if your model is a second order polynomial. So if your model isn't a second order polynomial, then you can think of it as a polynomial through Taylor, and you have an error remaining. Okay. So if you rise the order, then if you are matching not only the second statistical moment, but up to the third, fourth, fifth statistical moment, then you are able to have an exact estimation of the mean if the model is a fifth order polynomial. So this means that you are taking into account more pieces of the Taylor expansion.
So it's the forecast that's really improving. Am I understanding that right? By doing this before you have the forecast, you get a better forecast, and then because you have a better forecast, then you get a better analysis.
Exactly. You have a better forecast and a better approximation of the covariance of the forecast, then you have a better analysis. And if you use the sampling a second time, then you have a better likelihood covariance, that is which we are computing when we do R times Y. So both the pieces are better, then the result is better.
And we have time for a final question. You can discuss the break. So let's thank our two speakers for this session again.
Right, without food, so there's probably.
Better results on the mono experiments.
Yeah.
And worse on the ones that just written. For me, that's pretty counterintuitive as any.
It's not worse, just not effective.
Why that? Because usually I got the feeling that when you use integration, and observer part, then the whole idea of the common field it makes it, it makes an impact, and it has a less impact on the module does, and basically you don't get that much information in the simulation process. I thought about it now, it's contraintuitive. So I don't know what might be the reason for that.
Yeah, actually, I don't have, I'm not sure about the answer, but I can guess. My guessing is that, first of all, you need
I guess they can
you
actually
need a much
hear us.
better coverage.
So if we stop the sharing, then they can hear us. So let's just see before we start the next, yeah, before we start the next session. Annika and Svetlana, do you want to test that everything is fine?
I can tap
We can check.
Yeah, you can tap to them.
Speakers
Yes.
are online already. I think, yeah.
The both are online or no?
Yeah, I have checked. I think they're online. You can talk to them.
I talk to them or just
Yeah,
just type.
you can just say something. I think they can take. Up to you. Yeah.
Hello, I will chair the next session. So for next two talks, and is Anika Voget and Svetlana Tavova. Sorry, are you online or right now? Sorry. Hello, Anika. Can you hear me? Oh, I will switch to the camera first, maybe. Hi. I can see you, but you are muted. Can you try to share your presentation? Just check. Wait. Yeah. Hello, Anika.
Yes, hello, can you hear me?
Yeah, I can hear you. Yeah,
Oh,
that's
okay.
good. The full voice is good. And can you try to share screen? Because
Yeah.
in the morning there was some people had a problem with sharing screen. Could you try?
Yeah, I tried already during the lunch break, but let me try again if it's still working. Can you see that?
Yeah. Yes. Seems good. Yeah, everything's fine.
Okay.
Thank you very much.
Okay, great,
Yeah.
great. Should I stop sharing or should I just keep it open?
Yeah, please stop sharing. I will contact to the next speaker, the one after you. To
Okay.
Yep.
I think you can just start introducing the speaker.
Anika, could you share your screen and the people are coming on seat and we will start soon.
Okay, all right.
Can you hear me?
Yeah, I can hear you.
Yeah. I will write a text to you after 20 minutes. Then, yeah.
Okay, I'm not sure if I'm gonna see this, but I will try to keep time.
Oh, yeah, I will see if. Okay, I think everyone come back. You can start. So the next speaker, Anika Voget from Environment and Climate Change, Canada. So she will talk about maximizing the added value of multiple observations. So the floor is yours, Anika.
Yeah, thank you very much. And before I start, I would like to thank all the organizers for being super flexible, because I actually wanted to be there in person, but there were lots of organizational issues. So I'm really glad that I can at least present online, although I would have preferred to be there on site. Yeah, today I will present a side topic that I'm currently working on, which includes a lot of equations, like probably all of our work does, but I would like to explain this to you without any equations, but really getting that you get the idea of what's behind all this. So let's start very simple. So on the right hand side, you see a statistical, like our background data set in a statistical space. And of course, in data assimilation, we don't have only our background state, but we also have an observational data set, which is at another position, like always, because yeah, we are not having the truth. What we can, if we have these two data sets, what we can actually calculate in a statistical sense is the innovation covariance, which is in this view just the line between the two data sets. But of course, given this, we don't know where the truth is positioned relative to this. So for example, the truth can be somewhere there, and the statistics related to the truth are the two error covariances of the two data sets that we have, background and observations, as well as the error cross correlation between those two, which is in this case the angle between the two lines relative to the truth. But of course, we don't know the truth, so the truth can be anywhere. I just picked up 3 different locations. It could also be on the other hand side or whatever. So basically, because we only have one innovation covariance given, but the other 3 statistics are unknown, this problem is underestimated. And of course, we want the idea why we want to have an idea about the error statistics is because if we know the error statistics, we want that gives us information where our optimal analysis is between the 2 data sets that we have. But in this case, the problem is underestimated actually by 2 degrees of freedom, meaning that we don't know where the truth is relative in both directions that we actually see. And even if we have some kind of idea where to put the optimal analysis between the 2 data sets, we would still don't know the analysis error covariance, which is actually the dashed yellow line in this case. So what is usually done in this case is assuming that the 2 errors are independent. In this graphical interpretation, that means that the angle between the 2 error covariances is a rectangle. That means that all possible solutions of the true state are along this cycle here. And again, this could also be on the other hand side, but I just draw a few examples here. So if we assume this, we still have an underdetermined problem, but at least we're getting closer. Meaning if we have some idea where the optimal analysis is between background and observations, then we know, or we get an estimate under the assumption what the analysis error covariance, so this distance looks like. So we can still move the truth along this axis, but we have only 1 degree of freedom left to solve the problem. I'm sure that's nothing new to you. That's basically data assimilation. It's just like from a different point of view. But now it gets a little bit more complicated because we're adding a third data set. So the plot on the right-hand side is now a three-dimensional plot where we have this blue dot as a third data set. And if we have three data sets, we can calculate three statistical innovation covariances between each pair of these three data sets. So we have three information on the system. In the same point, we have three error covariances, which are unknown. So the error covariances of each of the three data sets, as well as three error cross correlations between each pair of data sets, which are still unknown. So we still don't know where the truth is, of course, but if we now assume that the errors are uncorrelated or independent, then we can actually solve the problem in the three-dimensional space, because then the truth can either be positioned there with the three right triangles here, or on the other hand side. But it basically doesn't matter on which side we are looking, because we're only interested in the error statistics, meaning the length of the error covariances and the angles, which are the error cross covariances, which we assume in this case to be a right triangle. So in this case, we can solve the problem from the innovation covariances to get an optimal estimate of the error covariances of the three data sets. And for some of you, it might sound familiar because this is basically equivalent to the three-cornered hat method or the triple collocation method, which are well known since decades in certain geophysical applications. But while these methods are mainly focusing on scale-up problems, so to estimate variances, this actually works exactly the same way for full covariance matrices. But as we're talking about data assimilation, if we have the optimal error covariances of our data sets 1 and 2, we can actually get an estimate of the optimal analysis between data set 1 and 2, which would be located here. And this is equivalent to the cross-validation approach, which actually says that if we have a third data set, the blue dot, then the optimal analysis in theory would lie exactly at this point where the distance between the analysis which must be on this line is minimal compared to the third data set. And this is equivalent to being closest to the truth. But if we have these three data sets and we assume that they are all in the same state space as we do in this example, we can even go further, because we cannot only calculate an optimal analysis between data set 1 and 2, but we can actually do the same between data set 1 and 3 and between data set 2 and 3. And then we get similar results. And we can even go one step further and combine all three data sets that we have to an optimal analysis. And I call this like triple analysis because it includes all three data sets, because we have all three error covariances. And this triple analysis is actually the point, the linear combination between the three data sets that we have, which is absolutely closest to the truth. I don't know if this is visible because it's three-dimensional, but it's actually quite fun to have this as a three-dimensional shape, and you can show that this is actually the optimal combination of this that we get. And this also implies that including all three data sets in the analysis is always provides a better solution than combining only two of them, as long as the assumptions that we have are more or less fulfilled, and as long as all errors are larger than 0, which we just assume that this is the case. Okay, in order to sum this a little bit up, we saw for two data sets, we have one innovation covariance between them. We have, of course, two error covariances for each data set 1, and we have one error cross correlation between the two data sets. And the sum of the error covariance and the error cross correlations is the amount of unknown statistics that we have, while the innovation covariance is actually the known statistic that we have. So given this, we can estimate one of the statistics because we have one innovation covariance known. If we would assume independency between the different data sets, we can reduce by one information because we have one cross correlation, which can be assumed to be independent. So in order to close the system, there's one assumption still need to be made. if we have 3 data sets, all values are free basically. So 3 data sets, 3 innovation covariances between them, 3 error covariances, 3 error cost correlations, 3 estimated statistics that can be estimated, 3 statistics which can be neglected when we assume independency. So the system is fully determined. We can actually estimate all the error covariances and we don't need additional assumptions. This table looks quite complicated or confusing, but it actually becomes much clearer when we plot this information for any number of data sets that we have. So on the x-axis, you see the number of data sets. And the gray line, I, is basically the one-to-one line, which is not only the number of data sets, but also the number of error covariances that we have in the system for each data set 1. And then we have the green line, which is the number of innovation covariances, so the number of pairs that we can create between the data sets. And it's also the number of error cross correlations and number of statistics that can be estimated. The orange line is the sum between the green line and the gray line, because this is the total number of unknowns that we have in the system, being the sum of error covariances and the number of error cross correlations that we have in the system. And then we have the blue line. And the blue line is basically the difference between the number of statistics that can be estimated minus the number of error covariances that we have. Let me try to explain what that means. Let's take the example that so the number of data sets I is smaller than 3, like if it's the case for 2 data sets, then the number of error covariances is 2. The number of statistics that can be estimated is 1. So green minus gray is -1, meaning that there's one assumption remaining, which has to be somehow assumed to close the system. For 3 data sets, these lines meet here at this point. So the difference between the 2 lines is 0, meaning that if we assume independency between all data sets, the system is closed and we can actually calculate all the remaining error statistics. But now if we increase the number of data sets to something larger than 3, then the number of statistics that can be estimated actually exceeds the number of error covariances that we have. Meaning that if we would assume that all data sets are independent from each other, we would get an overdetermined system, which can be solved. But instead of solving an overdetermined system, we can actually drop the assumption that the data sets are independent for some data sets. And in this case, this blue line D gives you the number of cross correlations that can actually be estimated by the system. So we don't have to assume these. We still have to assume some, but not all of them. And what you can nicely see is that that D increases quite fast with the number of data sets, which is quite promising. And for example, if we take, for example, I equals 5, so 5 data sets, then this D divided by N gives you actually the ratio of the relative amount of cross correlations, which can be estimated. And this is 1/2 in this case, meaning that half of the error cross correlations can be estimated, while the other half still has to be assumed to be 0, for example. And if we even go further and go to 7 data sets, then 2/3 of the error cross correlations can be estimated by the system. That sounds quite good. So the relative number of assumed error statistics reduces with increasing number of data sets. So we always can estimate more and relatively more and more statistics. But actually I have to say the absolute number of assumptions that are required still increases. And this is actually also I, so it's also the gray line. So the number of data sets that we have is equal to the number of assumptions that we have to make in order to close the system. So we will never be able to close this system without any assumptions. And if we now go back to the 3-dimensional plot that we saw here, we already saw that of course, combining two data sets with an optimal analysis, we're getting closer to the truth, assuming that the assumptions are more or less fulfilled. And if we combine even 3 data sets, we even get more closer to the truth. And that's also the case if we have more and more data sets, meaning that the more data sets that we have, the closer we can actually get to the truth. Again, assuming that our assumptions are more or less fulfilled. But it also means that we never really reach the true value as long as the error the error covariances are not 0. Okay, this was like about the general framework, but now you can think of different ways how to set up your problem, because you have to assume some error cross correlations while others you can estimate. And it has also already been observed in literature that not every setup, so defining which ones you want to estimate and which ones you have to assume, not every setup provides a solution. But up to now in literature, this was only observed for certain setups, and there was no real structure of what's possible and what's not possible. But actually, it's not that difficult if you think of it as like that. So the minimal conditions for a setup is that 3 data sets have to assume to be independent. And on the right-hand side, there's an example for 10 data sets where the gray line between the data sets just indicates that you need to assume that these are independent. So for these 3 data sets, I call it like a basic triangle, because actually you have to assume independency between all pairs of them, which create a triangle in this visualization. And then for every other data set, you have to assume independency to one prior data set. And I call this reference data set. Meaning, for example, data set 4 needs to be assumed to be independent of one prior data set. In this case, it's assumed to be independent of data set 1. And the same for all others. So for example, data set 10 is assumed to be independent of data set 9. Data set 9 is assumed to be independent of data set 7, and so on. And this structure looks very like a tree structure. So I call it like an independency tree, because you're very free in selecting how this tree looks like. You can have different branches, can have long branches, you can have everything, whatever you like. The most important thing is that everything has to be somehow connected to this basic triangle, and you have to have this basic triangle. That's the general conditions that you need to be fulfilled. But of course, if we apply this to real data sets, our assumptions will never be 100% accurate. And actually the accuracy of the solution from a certain setup is of course determined by the accuracy of the assumptions that we're doing. And the uncertainties related to that are proportional to the neglected error correlations that we assume to be 0, which is kind of clear, but you can show from the equations that there's no general increase of uncertainty along such a branch of independency. So we have changing signs in the contribution, meaning that there is the possibility that uncertainties are canceled out along a branch. So it's not a problem if you would add more and more data set along a very long branch. It always depends on the setup, but there's no general disadvantage of doing that. But of course, you want to have the best setup. And if we assume on the right-hand side plot that the distance between data sets indicates the true independency. So if data sets are far away from each other, there's some kind of really independent from each other. And in this case, the upper right-hand plot is not the best solution, but an optimal solution would be to set this basic triangle between 3 data sets which are far away from each other. Far away, meaning that we are quite sure that these errors are really uncorrelated. And given this, again, we start to connect all the other data sets to this basic triangle, and it might look something like that. I know it's like very confusing, but it's the same basis as above, but just trying to maximize the distances between the data sets. And another thing that you can do actually, if you also can assume, for example, that data set 4 in this case is not only independent of dataset 1, but also independent of dataset 2, you can build another triangle between these three and do the same estimation as for the basic triangle. And you can do this as often as you want. And the question what's better is actually depending on how certain you are in your assumptions, and you can do some calculations on that, but it gets quite complicated. Okay, with this I will come to my summary. Regarding the error estimation, we see that if we have co-located data sets, we can actually estimate statistically optimal error covariances. And I stressed the word matrices here because you can really get full error covariances, or full covariance matrices, including correlation and everything, given that the assumptions and sampling errors and everything related to that are more or less good. And I've been talking about the word data set a lot. This can actually be any kind of forecast, observations, even kind of climatology, whatever information you have. So for example, you can use this for comparing different forecasts, and you can actually estimate not only the error covariances of the forecast, but also the correlation between the different forecasts, if you want to do this. We saw that the number of estimated error statistic increases if we have more data sets, but there are always some assumptions that remain to be done. Two things that I didn't show is actually it's not necessary to assume independency, so zero correlation, but you can define any kind of correlation that you're thinking of. So if you have some kind of idea how two data sets are correlated, the errors of two data sets are correlated, you can use this information too. And you can not only estimate the error statistics from innovation covariances, but also from innovation cross covariances. And you basically end up with the same statistics with some small advantages, disadvantages, but it actually contains the same information. It's not shown here, but I will show this later on. And just a very short thing about data assimilation, I would say in this regard, we cannot have too many information, too many observations, too many data sets. But I will come to this back in a minute. And about the things I just showed you today, we're about to submit a manuscript. And the title will be How Far Can the Error Estimation Problem in Data Assimilation Be Closed by Co-located Observations? But I just want to take another minute to tell you some remaining problems that I was thinking about. So, of course, the things I showed you are very, very suitable for the increasing number of overlapping observations and data sets that we have, for example, in atmospheric science. But this is actually a problem for current data assimilation systems because they are tailored to have two data sets. So we have one observation state vector and one model state vector. And everything which is overlapping is actually thinned out in current data assimilation system. And I'm currently working a little bit on looking into generalized analysis equations, which at one point include multiple data sets. So really having an optimal analysis between more than two data sets, but also including cross correlations, because as soon as we can estimate cross correlations, we can drop the assumption also in the data assimilation system that the errors are independent, which makes the equation much more difficult, but it gets hopefully much better the result. Another thing is that, of course, real data sets are never fully spatiotemporally co-located. And that's actually an assumption that is made for all the things that I presented to you. But there might be a chance to still estimate optimal error statistics, even if the data sets are not fully co-located. I have some ideas about that, but I did not have a very detailed look up to now if this is really working and how far this can be applied in reality. And one other assumption related to this approach is, of course, it's a statistical estimation. So it requires that the error statistics are the same across all realizations, so for example, in time. And for many real application in geoscience, this is not the case because the errors are varying a lot temporally. So it might be an idea to combine these statistically optimal error correlations with some kind of flow dependent errors like from an ensemble or other methods. But that's also future work. And with this, I would like to thank you. If you have any questions, ideas, comments, or concerns, feel free to ask me. You can always write me an email or contact me. And I will also be in person available next week on the on the ISTA in the US. So if some of you are there, I would be happy to talk to you in person. Thank you.
Yeah, thank you, Annika. I think we have 4 minutes for some questions, maybe 2 questions. Yeah, go ahead.
Thank you for the great presentation. A question, because at least the way you presented it, and I might have been wrong, is that like it seems to focus more on the data sets being more observational sense in the data set, or like that if you have overlapping observations or so forth, and feel free to correct me soon if I'm wrong. But out of curiosity, how do you feel using, like based on how you presented here, how do you feel about using 2 models as independent data sets for 2 model projections as independent data sets for assimilation within the structure you presented here? And can you ever really consider those independent in the sense that do those assumptions you framed here still hold valid in such a situation? This is more of a theoretical question.
Yeah, I'm not sure if I understand your question correctly because of the sound, but do I understand you correctly? You were asking about how to include different model forecasts and how valid the assumption of independence is in this case. Is that right?
Yes.
Okay, good. So the good thing is that you don't need to assume that they are all independent. So for example, if you have one observational data set, like in situ observations, where you were quite sure that the errors are independent from all the model forecasts, then you only need to assume that 2 model forecasts would be independent, and all the other dependencies between all the other model forecasts that you might want to include can actually be estimated. Does this answer your question?
Yeah, somehow. Yeah, thanks. Other question? 2 minutes.
Thanks, and Anita, can you go to the 3-dimensional like that geometry, the triangle case? If I see it correctly, I think the triple analysis point is kind of equivalent to sequentially assimilating the 2 data sets, one by one after the another. Is that true?
Yeah, exactly. That's one thing that that you can actually show that if you have the optimal analysis between 2 data sets and you combine this optimally with the 3rd data set, you actually end up here. And it's the same if you start this the other way around. So you can sequentially assimilate more and more data sets in kind of a iterative structure, and you end up with this optimal triple analysis.
Yep, thank you. I think we'll have to move on to the next speaker. Annika, could you stop sharing? Thanks. The next speaker, Svetlana Trevova from Hydromet Center of Russia. Svetlana, are you here or are you ready? Can you share your screen?
Hello, yeah, I'm here.
I'm
ready.
Yeah, can you share your screen?
Yeah.
Yeah, it's there. It's not the full screen.
Is it okay?
Now it's fine. Yeah.
Okay, good.
The floor is yours. Yeah.
Thank you. I present research dedicated to the future soil moisture analysis system for the Russian global atmosphere model SLAV. So I will first tell you about atmosphere model SLAV, then our multi-layer soil model, a simulation for soil moisture for this model, the challenges we encountered in the process of implementing, and show some numerical experience. The Global Atmospheric Models Lab is developed by my supervisor and Tolstych Mikhail Andreevich and our colleagues. It's used for operational forecasts in hydromethane of Russia. Model has original dynamical core. Most of the physical parameterization are borrowed from LR consortium. Also, SLAV includes some of our developments. One of them is multi-layer soil model. Presently, soil processes are described by the multi-layer soil model, as I said. This model was developed in Institute of Numerical Mathematics of the Russian Academy of Sciences and Lomonosov Moscow State University. This land surface model has already proven itself in another Russian climate numerical model. The system of soil equation is presented on the slide. Thermohydro transfer equations are one-dimensional and are solved at each land grid point separately. The model has 12 layers. 4 of them are reserved for the snow cover. The soil equation system is solved using finite differences in space and an implicit time integration scheme. This soil model requires initialization of soil dataset. It is known that screen level temperature and relative humidity depend on surface temperature and humidity too. The last are controlled by soil moisture through the transpiration flux. Considering the lack of global direct measurements of soil moisture, we decided to assimilate screen level observation for analysis of soil state. For this purpose, we have chosen simplified extended Kalman filter method. It is well known in the world and especially in soil state application. And it's relatively easy to implement comparing to other, but because it has advantages and disadvantages. This filter isn't the Kalman filter in a classic way. It's closer to dynamical optimal interpolation. The main equations of the simulation method are presented on the slide. In a common way, this method can be implemented for many layers. Our soil model has 9 levels, but due to limited numerical capacities, we consider it to implement this algorithm only for 2 of them. This method has 2 assumptions. The first is neglect of horizontal connection between surface and atmosphere. Thus, we can solve equations in each soil atmosphere column separately. And the second assumption is the observation operator can be linearized. For this study, the control vector contained the 2 main prognostic variables, the water content at n and n+1 levels. The observation vector consists of screen level temperature and relative humidity observations. Matrices B and R are constant. The simulation window is 6 hours. So during the realization, we faced with some methodological and technical challenges that linked with observation operator. Mostly, it is known that assumption of its linearity is not always fulfilled. So for this reason, we used the double evaluation of Jacobian components. The element of observation operator are derivatives of screen level temperature and relative humidity with respect to soil moisture. They're estimated by the finite differences. One side finite differences, and after that we average them. So to better estimate linear regime, as I said, the Jacobian computed with negative and positive perturbations. So the total number of model runs in the simulation cycle is 5, because we need plus positive and negative runs for one layer. We have 2 layers. It means that we have 1 control run and 4 additional. And actually, it is too expensive for operative use. That's why we made a so-called offline version of the land surface model for additional runs. Offline land surface model is the model that can predict soil state without full inclusion in the atmospheric model. To evaluate screen level variables, we need the states of the surface and of the lowest model level. It was demonstrated in some articles that for estimation of Jacobian components, we can neglect influence of soil moisture perturbations on atmosphere above the lowest atmosphere model level. So in our model, surface has been externalized from the atmospheric part. We force offline land surface scheme with atmospheric forcing that was got from the full model run. The first atmospheric level is around 17 meters. Soil and the low part of the boundary layer will evolve, and we get prognostic soil state at surface. And then these variables vertically interpolated at the screen level height. So this setup retains the dependence of screen level parameters on soil variables that is required for this assimilation. Thus, this approach greatly reduces computational costs of the system compared to the full atmospheric model, approximately 1.5. So at this slide, we have the scheme of the assimilation systems. To assess the Jacobian elements, each considers states, each considers soil moisture level at initial time is perturbed by a small amount of soil moisture. Then we make one model run from undisturbed state and write the atmospheric force. After that, we launch 4 additional runs with an offline land surface model to get an estimation of the linear observation accurate. We get 4 additional background states, and after that we can estimate a linear observation accurate. Then, as our background and observation errors metrics are constant, we can find a Kalman gain matrix, and analysis equation can be solved. The resulting soil analysis are used to launch the atmospheric forecast for the next assimilation window. Using offline model, we found how we can relatively cheap calculate of observation accurate, but as we can see on the slide, assumption of linearization is not fulfilled ideally. So to determine the fraction of the nonlinear part to the Jacobian SS, we calculated difference between the derivatives and took the ratio of the second order component to the sum of the first and the second component at each good point, and after that average them globally. So we did that for different soil moisture perturbation. As you can see, for 3 soil levels, we chose them because they has the greatest influence on the atmosphere. The main connection between soil moisture and atmosphere is supposed to be using transpiration flux. That depends on route. The route distribution isn't uniform with depths in our model. The Biggs route concentration are set at the 6, 18, and the 54 centimeters. So we have checked the behavior of the observation apparatus only for these layers. And at the slides, you can see the sensitivity of Jacob. It's not sensitivity, it's a ratio. It's a part on nonlinear part in the elements of Jacobians at different levels, as I said. And we found that in our model, the operator is well linearized in the narrow ranges of perturbation. You can see that the smallest nonlinear part we have only here. For relative humidity, it is almost the same ranges. We obtain an increase in nonlinear part for size of soil perturbations higher than 1% of soil wetness index and higher than 6% of soil wetness index. So, but we can say that if we choose the soil perturbations from this range, then okay, we can consider, we can say that our operator observation can be linearized. So after that, we determine these ranges. We know all components of Kalman-Gain matrices, and we can realization of our soil assimilation. We made a couple numerical experiments. In the first of them, we tried to assess relative humidity observation impact to soil moisture analysis and screen level forecast. I mean that, as I said, observation operator can have 2 observations, as screen level temperature and relative humidity. In that experiment, in one calculation, observation operator has the only temperature, and in the second experiment has both temperature and relative humidity. And what we find that when we use both observations, the average monthly moisture increment in soil column is bigger. So we have a greater influence, greater effect using such analysis in a forecast. So we took this analysis as initial data for the forecast of model SLAV, and we tried to estimate what happens with the screen level forecasts when we use this or this analysis. And we find that using not only temperature, but also relative humidity can decrease root mean square errors and bias in screen level forecast. You can see at the slide the estimation in 3 regions: North America, European part, Russia, and Asia. The second experiment was dedicated to assess influence usage of soil moisture analysis compared to the lack of them. Again, we compare two twin experiment. In the first simulation, the initial data have analysis soil moisture, and in the second, it is just soil moisture background field. We didn't have any soil analysis, and we called this experiment open loop. So again, the analysis scheme have been tested for July 2014 globally. The estimated regions are displayed this. So we can see that the soil increments have mostly positive sign that indicates bias error in the model physics, which leads to soil drying and overheating. Also, we see that using analysis improves accuracy of screen level forecasts in comparison with open loop run. Root mean square errors decrease up to 0.7 dB in North America, and up to 0.4 in Russia. Biases of both regions decrease too. Also, we found a positive effect in Australia and Africa, but these errors I don't show there. As a conclusion, I can say that we have a realization of a simplified extended Kalman filter for soil moisture analysis using screen level variables. In the frame of this analysis, we developed an offline version of the land surface model for the initialization of soil water content, a numerical weather prediction model. Validation of tangent linear hypothesis for observation operator shows that from 8 evaluated layers, the best results are obtained for levels with depths 6, 18, and 54 centimeters. And the first experiments with the system show improvements of screen level forecasts up to 19 hours lead time in different regions of the world. Optimistic results of soil analysis usage for short and medium forecasts led to long-range forecast experiments. So thank you a lot for attention.
Thank you. We have 10 minutes for questions. And any question?
Yeah, maybe I can ask one.
Yeah,
So
sure.
I noticed that you mentioned the use of simplified extended Kalman filter. So what's the advantage and the disadvantage in comparison to?
Yeah. So actually, in soil moisture, there is some method are very popular. It is ensemble Kalman filter and extended Kalman filter. Ensemble Kalman filter is very cheap compared to extended Kalman filter because it requires a lot of ensemble members. So we decided to use extended Kalman filter, but after reading a lot of works, we found that in some papers in Meteor Friends, Claire Draper showed that using dynamic matrix B did not help to increase quality of analysis soil moisture. And further, in European Center of Medium Weather Forecasts and in Meteor Friends 2, decided that if they choose matrix B as constant, then they did not lose a lot. And this simplification And due to this simplification, the extended Kalman filter now called the simplified extended Kalman filter. So the main advantages, it is simplicity and relatively cheap. For example, compared to ensemble Kalman filter. From disadvantages, as I say, that assumption of linearization of observation operator is not fulfilled very well. So we tried to do something with that, but it is hard and it is not universal. No, not universal. It isn't. We can guarantee that in each grid point, this linearization will be very well. That maybe it is the most disadvantages of this method.
I got it. Thank you very much for the presentation. Oh, there's one more question. Do we have time now?
Yeah, we have time. Laurent?
Thank you, Laurent Bertineau. I would like to know what would be the main shortcoming of the atmospheric data you have used. Is it problems with the temperature, the winds, or humidity?
I'm not sure that I understand you correctly because you have a lot of echo. But as I see, you want to ask about effect. So where we can find the most effect from the user analysis, or no?
Wondering if you would want, say, a better atmospheric data for your work, what should be improved?
What should be improved? Okay, I see. Yeah. Of course, it should be improved screen level, temperature, and humidity because of physics. Also, you can expect that forecast in the upper atmosphere. I mean, for example, at 1 kilometer, 3 kilometers, temperature and relative humidity can be better due to better soil analysis. I'm not sure that it can influence on the wind, for example, or pressure, but in the thermo-hydro variables, you can expect the effect from that.
It's fine. Akhilesh, question.
So actually, I had a question regarding the assimilation approach. So since we are using soil temperature to update, screen level temperature to update soil moisture on a global scale. So it is possible that the soil moisture might not be a driving force for screen temperature on a global scale on certain regions.
Yeah.
So do you any study or any plots which shows that it's not working over these regions because of that?
Yeah, you completely right. So we have assumption that soil moisture is errors in soil moisture is the main cost of errors of screen level temperature, but it works not in every situation. For example, when we have a strong wind, rain, I don't know, a big cloud or something like that, this assumption doesn't work. And due to this, we can analyze such grid point. That's why it is not very well. And from this side, we don't have a very big improvement, a very big advantages compared to optimal interpolation, which works in that assumption. So yes, there is some atmospheric situation or soil processes as melting or freezing, when this method will not be work.
Yeah, thank you. Any further questions? Yeah, I think that, thank you, Svetlana.
Thank you very much.
I think we are 5 minutes ahead the schedule, so we have a 20 minutes break or okay. So we have a 20 minutes break, and then for I think for online speakers, maybe it's better to you test the first the and the microphone and the share screen with us, and then because they do have some issue this morning. Yeah. Yeah. See you later.
Oh, that's a move a little bit. You are the session chair.
Am I again?
I mean, or
that's the
yeah,
but I think you get the network cable.
Network cable.
Or you want the Wi-Fi here?
No, what do you mean? You want to upload your?
No. This is forget this.
Okay.
For the connection.
Yeah.
Sometimes it's better if you have the cable rather than using the Wi-Fi.
Oh, okay. I'm not sure if there's any. Yeah, maybe I will check that later. Or do you have time? Can you, if you have time?
But, I didn't see any problem with it.
Yeah, I didn't notice, but Rohan said sometimes the network's not stable.
So are you checking with the speakers for the next session?
Yeah, you are the. Oh, okay. Yeah.
I don't know.
You are the.
Patrick
Yeah, you can do
will
it. Patrick will do it. Patrick will do
Patrick
it.
will do it.
I need to. You are the session chair.
Checking with the next.
Yeah, just check if everything works, like the ability to share the screen
And the sound.
and the sound. Yeah, exactly. Because we have problems this morning.
Just a minute. But I can find the wire.
Yeah.
Upload.
Yeah. Sure. Oh, what's the Lohan?
But I have.
Lohan took it. Yeah. Okay, that's good. I think Lohan took it. We said forget about that, then it's gone. Yeah, is this one?
That's the one.
Okay, good. It's a PDF, right?
Yes.
Okay. I will just copy it. Let's see.
Okay.
Jack, let me open the file. Yeah, I think
Okay,
it works.
yep.
Yeah.
There's no movies or anything. It should be fine.
No, I think it should be okay. Okay.
Yeah. The guy is on holiday today. Should I call him in to ask for cable? Or
Maybe
should
you
we
just
wait?
go to reception because there's another replacement. You know
We
that.
don't have a problem with this.
No, we don't have a problem. But when he is back, I think I can talk to the reception.
No, I can do that.
Just
But,
ask
it's
them.
just that something they also want to know.
Yeah.
So I was wondering, why do you like leave 2 hours free time the last day?
We make some time for food, right?
Food, okay. What kind of food? Okay, so you want to have food in the restaurant?
Maybe, they have some time to have some food before boarding, but I don't know. That's up to them. Because we already fill up the program and then I don't want to change it.
No, I know. But there is 2.5 hours
Yeah.
free time
Yeah.
before you go to the boat.
Yes.
And
You want to move a session there? Yes.
I mean, in a way, we should have done that because what's the point? People cannot run and shower and
I want to change it because they have already seen the program. If you change, then you might.
no, there's no food ordered here. There's no food ordered
on Thursday.
On Thursday.
I talked to the man. He said you ordered something on Thursday.
Only lunch.
No, I think he said, do you prefer like have some spaghetti? Did you talk to him?
Spaghetti?
Yeah.
He
said,
asked me, do you want a baguette or a wrap for the boat?
yeah, maybe that's what he meant. And then I said, oh, it's good to have something to bring with us on the boat. So I saw that you have already decided.
No,
no,
I was really wondering
not
what
spaghetti,
is it?
but yeah,
what is it that you want to do? I mean, I'm not here, but people are not maybe hungry 1.5 hour after lunch.
Yeah, that's what
So
what
they are
that means
not
that in between we have 2 hours, then we could have something to eat. That's my initial thought.
Okay.
So I thought the guru has arranged some food before we leave. But now I got confused. I don't know, do we have that on Thursday or not?
No, so I have communicated with Guru today.
Yeah.
And I will check it again, but no.
Yeah. Please, because now I'm a bit lost. Yes, that gentleman, he said you and him, you reached some agreements. Yeah.
I was just wondering about your plan for those 2 hours.
Yeah, I have been thinking that maybe we can have some food before we leave. But if people want to take the food on the boat, that's also okay. And then we will have 2 hours.
So we have 2 hours left.
And as just have a break, it's okay. Like to have some break without anything. We can just sit here and chat a little bit. Actually, the weather is not so nice, I guess, on Thursday.
So Thursday, we only have the first break with coffee, tea, and cake. And then we have 12 to 1 lunch.
Yeah.
And then there's nothing else. And then we have to add it.
Oh, we have to add it. I saw the guru booked that. But why do we cake today? We have 2 rounds. We have fruits and the cake. Is that correct today?
We have cake now.
Yeah.
And we have tomorrow.
Tomorrow we have nothing.
Tomorrow we have only coffee.
Yeah.
And then Wednesday we have cake for the early lunch. We have fruit for the late break. I mean.
Okay, that's
yeah.
Because
it's a very long day.
Yeah.
So then we both have cake and fruit again. And then Thursday we have cake before lunch.
We have cake before lunch.
Yeah.
Wow. Why not?
Why not take so there is a lot of food, but I don't think people will be ready to eat.
No, I mean.
Right now, there's no cake or no. I mean, at least I just came back from there. There's no issue of some sweet stuff.
Okay, let's see.
And we will not pay. They don't pay.
I think, yeah, you will do it because I'm trying to download some slides for people presenting, but you need to check. You need to talk to the speakers. I think one speaker is not yet here. It's like Tim Smith.
Is not online?
No, he plans to present online, but I don't know what's happened. There is cake. Okay. That's a good. Yeah, if I look at the list here, maybe I have what time is now? Yeah, I need to send. I need to send.
I'll just try to connect with him, and if he's not there,
Yeah,
then
just try to talk
I
to
switch the talks.
Yeah, you can switch. Yeah, that's correct. Yeah, that's a good idea. We can ask Vikram. I think Vikram. Yeah.
Yep.
Yeah. Yeah. I'll send an email to.
There is no wire network. There's only Wi-Fi.
And then.
That's what they say.
But Vikram isn't responding. He's still not there.
No, okay. I have just sent the email. And I think from maybe
Vikram
she.
is offline
I don't know.
until-
Yeah.
Until it's.
I don't know. Maybe he will show up. Have you sent me a message?
Yeah.
Just send me a message. I don't know why it's key.
So if Tim isn't there and Vikram isn't there,
And just Steve is. Steve is not here. That's the best. If both are there, then we can swap.
And then here, relax, but this is nothing. So many agreement that I can see. Yeah. I hope I'm not. But if I'm meeting, then
It's time, but we don't have any speakers.
No. So, is this yours?
No.
No?
No.
This is yours?
Neither.
I will take one. Okay, here's the case.
But then I will just ask the next guy to speak.
I can talk to Cam. Cam. The speakers in this session, none of them are only reminded to
Because I have your own slide.
Let me see.
Are you sure they are not here?
No.
It's in front, right?
Maybe,
That's
no,
the
no.
problem.
I sent an email, but I didn't get a response.
That's why hybrid and virtual.
Yeah, that's
that's
another fun.
If you're in person, you're committed. If
Yes,
you're not,
yes.
then maybe.
Exactly. And then they want to use microphone.
I can, if I have to.
I mean, maybe it's better.
But so they can hear him through the microphone.
Hello? The online people, right? We are here, we can hear you well.
I think so.
Yeah.
Somebody is reacting, so.
Is that the clicker? No, I think it's okay. Let me just.
Yes, I believe.
Okay.
All right, so now I have the pleasure of introducing Tom from the University of Texas, Austin. So the reason he's going now is because we couldn't establish contact with the two speakers that were supposed to go before him. So if you look at your program, he's second to last, and afterwards.
Hello? Hello? Sorry, I'm Vic. I'm here.
Okay, let him talk. Let him talk.
Are you not able to see my name at the top of the Zoom?
Pardon? Could you repeat that, please?
Are you not able to see my name at the top of the Zoom? Like so establish contact in the sense that did you send an email on Slack or where?
Yeah. I think
It's better for you to speak to him. I think we can just let him.
All right. So we're gonna go ahead with Plan B, where Tam will speak now still, and then go back to you right afterwards. Is that okay?
Yeah, that's fine. So I will talk at my planned time.
Yes.
Yeah. Okay. Thanks.
Great. All right. So back to Tam, and thank you for. Yeah.
Okay. Let's start. So I have 25 minutes, right? Okay. The speaker. I didn't mean to steal your talk. Okay. I was put in your position. By the way, so I'm a tourist here for two reasons. A tourist for Norway and also a tourist to this workshop, right? Because my research is more on English problem, uncertainty, quantification, and deep learning methods, especially how to incorporate physics in deep learning model and understand mathematical property of deep learning to solve inverse and UQ problem. And in one of the effort that I tried, I work also a lot with randomization technique. So I'm in an effort to unify a few randomized methods. I'm looking at ensemble computer, and it looked to me as a randomization, and it's not clear how to do it. And for spend a few hours so looking at from different way of approach. Then I'm going to share with you some of the thing that I found, especially mainly in optimization and duality perspective. And okay, so usual stuff, funding. So these are my students, Aaron from the left to the right, Aaron and Chris and John and Hai. So Aaron was the one who do optimization, and the rest are working on duality. So to put myself a little bit of perspective. I'm working on the sibling problem compared to data assimilation, but it's mathematical point of view, data assimilation, inverse problem, they are just basically the same thing, right? Especially when you look at 4D VAR. So let me just show you an example where I did in terms of inverse problem. This is the global seismic inversions where we saw on the form of the earth scales, where this is the Japan earthquake simulation there. So the Japan is in the middle. I don't have the pointer, but you can imagine. And then with the earthquakes, let's see how earthquakes actually propagate in the earth. And that's a forward problem where you know the earth property initial conditions and the earth source, earthquake source, then you can solve. But the inverse problem is that you can measure, do the measurements. To actually in the US, they have like 7 seismometer measuring the earth movement. The question is that what is the image of the earth, right? What is the material inside, where's the faults, so that you can hopefully anticipate where the earthquakes in the futures and volcano, things like that, right? And it's similar to the other imaging problem as well. Okay, so this is just an example where it is 10 years ago where we almost get the Golden Bell Prize in high performance computing. Golden Bell Prize is like an Oscar in computation, right? Here we solve a inverse UQ problem back then on about 1.7 million parameter. This is not linear inverse problem. The equation itself, linear elasticity is linear, right? But the inverse problem is non-linear. And so the left-hand side here is the synthetic true, and the white dot are the measurements, and the 3 point there, black dots are earthquake sources, and this is the reconstructions or the inverse solution. And what we are interested more on not only just give the solution like the weather forecast, but also uncertainty associated with the solutions. So we have the priors, and then we have the data is have information provided. And from the prior uncertainty and from the data informations, we can compute the posterior uncertainty, which is on the left. And as you can see here, the blue is the lowest value. So what you can see there's around measurements locations, the uncertainty is actually less, right? Once you combine the information from the data. Okay, so this is the type of application or problem that I'm working on. So what I'm showing to you today is on optimizations, and because that's my background on, and the first one is optimizations of view on ensemble common filters. So to put notation into place, the forward model, which is G, right? U is the parameters or log normal. Somebody mentioned log normal. U, you can see it. The whole thing e to the u is a log normal distributions. And what we are interested in to invert for the u, again, this is a prototype problem to put in the context, right? But for each u, you can solve that equation, which is one forward equation, right? Then you can do evaluation, which is G. So G is a parameter to observable map. And you have the data, and you have some noises similar to the data assimilation problem. But in general, we don't have to update, right? We don't do time history matching. We just have the data either in time or at the final times, and then we figure out what is the material property. So one way to do it, of course, inverse problem is to perform optimization. This is the PV constraint optimization that we have to solve. Okay, so just I think ensemble common filter everybody knows, so I don't have to do it. It's just a notation here. M is the dynamical for system by the forward map, and then H is the observation operators. But the rest is just the standard common filters and ensemble common filters. Okay, so like I said, it's not that I don't want to deal with data assimilation. It's just I'm more interested in ensemble on the inverse problem. The question is how do we actually apply ensemble common filter on the inverse problem? Remember, the inverse problem in general, there's no time stepping in there. You have measurements at the final time, right? Or for the steady state problem, there's no time dependence. You just have the measurement of the temperature. Let's say I have a measurement of the temperature on the surface at a few points. The question is, what is the conductivity? Was it right? There's no time. So that's the inverse problem. Or I have a measurement of temperature at 10th hour from now. The question is, what is the heat conductivity? So G is the forward map. U is a parameter that we invert for. So in order to try to, this is not our work, right? This is back to Andrew Stewart and his students. He actually, what they did is that they try to put that in the context of dynamical system. So there's a fake dynamics that they propose there, right? So they concatenate U and the forward into vectors. They call MZ. And what their dynamical system from Zn to Zn plus 1 is the second equation that I show you. The interesting part that Un plus 1 is equal to Un. So you actually, there's no dynamical system behind, right? Unlike the standard data assimilation, you have to push the particle or the analysis from the previous step through the dynamical system, you get the forecast, right? And then you do the analysis. So here, the forecast for U is actually doesn't change, right? And you see that we substitute UN into the forward model to get the observation P. So the P itself, the only thing changed here, or perturbed here is the noise. Because otherwise the forecasting doesn't change anything at all. And then you do it again, this is a fake dynamics. There's actually no dynamics, the real dynamic here at all, right? And then they apply ensemble common filter on this, and they do a lot of work later. But when I look at this, and actually I think it's interesting. And then the reason I was interested in that because ensemble common filter does not yield the gradient, which is nice, because otherwise to do PD constraint optimization, typically we have to use agile method, right? You use gradient and Hessian-based approach. It's expensive, but we have a way to deal with that. But I think this is kind of interesting type of thing. So we try out. This is nonlinear elliptic inverse problem. Remember that the problem that I show you here. This is the elliptic inverse problem here, right? Steady state, there's no time dependent at all. So we should try 1D and see what happens. So 1D with 32 parameters. So I discretized the domain into 32 pieces. So the hit conductivity is 32 at 32 points. And the true solutions and the measurement, as you can see, up there. All right. So if I use ensemble Kalman inversion, right? It is nothing more than ensemble Kalman filters. And as you can see, that's 15 iteration, 40 iteration, and until 10,000 iteration, then it shows something similar. So it's very expensive. No gradient information, which is nice. But then you have to, each time you have to evaluate the forward map, right? You have to solve PDEs. And if you're 10,000, I better off with the gradient-based method, right? Because otherwise this is too expensive. So
before you go, what was being measured?
I think I should have to say this is a linear problem instead. Okay, so the U is the red thing, which is the true, the U with the parameters. So G in this case, actually, this is not inverse. Now you're talking about it. So G is identity. G, which is the formal map, is identity. So that's a good question, Dean. I forgot. This is a different example. So you see, we do measurement. We add noises and there, which is the black. And then this is even for linear. That's the main point, right? Even for linear inverse problem, it's non-linear. And you do see that I have a lot of measurement there. And and you see that it takes 10,000 iterations in order to get the reasonable results. Okay. So that's ensemble Kalman inversions. So for me, from an optimization point of view, so the left one is ensemble Kalman inversion. Remember that I said that from UN to UN plus 1, you don't do anything. You just keep unchanged. The only thing that actually make the dynamic changing is when you do observation, where you add the noises. So you perturb the observation with noises, right? So for me, when I do optimization, we see, okay, this is like the optimization without gradient, right? So only function evaluation, and we know, right? It's very slow. If you optimization, and if you look at only function evaluation, you don't give any gradient information, it takes a long time to converge. So what we did is, how about this? I'm going to add alpha or negative alpha F there, right? And F, what is F? There's a lot of options here that you can see. And what is A? There's an A there as well. A doesn't need to be UN, right? So we have a number of options. The first one, the first line on the table is the gradient descents. So then we just simply take F as the gradient of the data misfit, right? And A, so then we have to evaluate for each particle. So U from I to 1 to N, right? Have N particles. So you can for each particle, you can just evaluate the gradient, which of course you see expensive. The second option is that the gradient-based mean. So what you do is that you only compute the gradient at the mean particle, the average particle, which is U bar. Okay, and the next level, which is the full Newton method, right? You take the Hessian inverse times the gradient, and then you evaluate at each particle. Of course, this is the most expensive method that you can think of. And then the next H mean is just the gradient, and the Hessian is evaluated at the mean particle, which is of course less expensive, but still expensive. And notice you never form Hessian, so this is a beauty, right? In optimization or PD constraint optimization, you never form Hessians. What behind the scene you do in exact Newton CG, and in exact Newton CG method only require Hessian time vector product, and Hessian time vector product can be do exactly and efficiently using adjoint methods. Okay, so we don't need, but when we wrote there, no, well, please don't be alarmed because it's not, we never actually form the Hessian at all. And then the last two option is, you try to approximate the gradient in some sense, and that's our way to approximate. It doesn't look well. I mean, as you can see, it doesn't show very good results. Using some sort of information is better. So what I'm showing you here is the true parameter, which is the heat conductivity on the thermal fin, as you can see, right? There's two Gaussian block there. And I have a measurement on the fin, the temperature on the fin, and I want to invert for the heat conductivity, which is the profile on the figure A. So in the middle, with the B, figure B is ensemble common filters with the fake dynamics, right? Fake dynamics with 10,000 iteration. And I forgot to mention. So we have 50 particle, and the number of parameter that we want to invert for is 1,300 parameters. C is the gradient base with the 100 iteration. You see that with the gradient base, it's actually improved significantly. And notice that, remember that gradient based approach, gradient descent approach, you have to compute the gradient for each particle. So we have 50 particle gradient, 50 particle at every iteration, and you multiply by 100. So that's not expensive. So but the mean here is actually less expensive. You just take the computed the particle means, right? The mean of the particle or ensemble mean, and then you evaluate the gradient at that mean only, and then you move everybody in the gradient that same manner, right? With that one single gradient. You see that this is 101, so it's not different, but it's of course much cheaper. And then this is the Hessians. And you see the Hessian is different, right? If you do Hessian, you actually converge faster to the means. And of course, and you want to see, I'm not going to show here. This type of approach is only useful if you care about the mean or the predictions of one prediction. If you care about uncertainty, then this is not good, right? Because all particles try to move to the maximum a posteriori point, right? The maximum or the optimal points. So it's try to converge there, and if you estimate the covariance, anything like that, it's actually not good. Right? All right. So this is H means is the Hessian evaluate the mean, and again, it's not different, but this one actually cheaper than this. And the main point is that in this slide, the different methods doesn't matter. But what I'm trying to say is that ensemble common filter, if you care about the optimized or the best estimations, then adding some sort of information about gradient is actually a good idea. That's all I want to tell. And this is 3D version of that. The true parameter is like 3 lobe, right, underground, thinking about like, you have sand waves inside the earth and see whether there's oil reservoir if you want to see that way. And on the right, I show you is ensemble common filter with 50 iterations, and it's still messing around. It doesn't know where to go, right? But if you do the gradient, the mean, sorry, there's a typo here. Then you see that if 50 iterations, you already see the 3 block there, and the Hessians, of course, even with 15 iterations, you already see the thing very well. But again, it's much more expensive. But if you compare, right, it's expensive if you compare. If the currency for us, the currency is the number forward solved, because the adjoint and the forward is pretty much the same. But the adjoint much faster, of course, right? Adjoint is only linear problems. But let's say we make add one add forward, one adjoint is the same. Then 15 iterations. If you turn into a number forward evaluations compared to the ensemble common filter, depend on dimension, it could be much less, right? Okay. Of course, we look at the theoretical thing about view a little bit, but of course, it's for only linear forward map. If you have a linear forward map, then if you forget about noise, if you have a noise in the limit, and this is not in the limit of the infinite number of particles, this is finite number of particles, but the limit in terms of times, because each time step in, right, iteration of the ensemble Kalman filter, you actually can associate with the time discretization, like forward Euler of the stochastic PDEs. And if you take that time limit go to 0, you will recover the stochastic PDEs. Right? There's that ODE. Sorry, there's stochastic point. If you incorporate a noise, then you have the Brownian noise there. But for the purpose of demonstration, I look at the dripping term. Okay, so the gradient step is the one with optimization. Without optimization, alpha equal to 0, you don't have that term. The ensemble Kalman filter is still a gradient flow, which is nice, right? So that's why it worked pretty well in practice, because a gradient flow, it tried to get to the optimal points. That's the first term. That's the ensemble Kalman filter, traditional one. But if you add the optimization or gradient information, you have a second term. So it's going to accelerate, right, the conversions to the optimizers of when you have a second term. Again, it's actually consistent with what we try to do, right? We just add a gradient so that we can go to we add all the particle to move to the optimizer faster. Okay. And actually another thing, actually analysts do have proved something interesting. If you use ensemble Kalman filter in the context inversions, I'm not sure about in the data assimilations. If you affect dynamic, I think it should be maybe the same as well. The subspace spanned by particles, regardless of nonlinear or not. After you do forecast and update analysis, you get a new particle, but the space span, the linear combination of these, right? Look at the vectors. Then the space spanned by each of the ensemble is the same, regardless, when you move from one step to another. So when you add the gradient term, the gradient information like we did, actually we can escape that subspace. In other words, ensemble Kalman filters, it's important that you choose the first set of the ensemble very, very nice, right? Very good, because otherwise it would because on the particle always stay in the same subspace. But if you do this, you can escape the subspace to hopefully get a better and this may be explain why we get better result within a few iterations. Okay, so that's the first thing that I want to share with you from optimization. One way to look from ensemble Kalman filter. And like I mentioned to you, I try to unify a few points. Started with the work with Dean that on the randomized maximum likelihood. I worked on that a few years back. Now I try to unify a couple of things, and I'm going to ask myself, how can we look at the ensemble Kalman filter from the randomization, right? Randomization. Okay, so what I did is I'm looking at the linear problem only. So the forward map is AU. And what I did here is actually very, very strange, right? Because if you replace B as AU in there, you get the linear inverse problem. There's nothing different. What I actually do, weird thing is that I do a substitution or introduce a new variable V, which is AU. I convert unconstrained optimization into constrained optimization, which is crazy, right? Because constrained optimization is always more difficult, but it's just for the purpose of derivations. And if you do optimization duality a lot, you can derive a dual problem for that constrained optimization. And how do you do just simple Lagrangian approach? And then you get to a dual function, which is I'm not going to go into detail, but it's just the minimum of the Lagrangians. Don't worry about that. It's a dual. The interesting is that the standard optimization that you do, they typically call a primal problem, and that's not the associated problem with the primal. We call it a dual problem. And an interesting fact, typically you have weak duality. That means at the optimal, the primal objective function is always higher than the optimal of the dual problem. If you have weak duality, if you have strong duality, then they are equal. And the beauty is that if you do this, typically the dual problem is easier to solve, typically, right? Dual is like an adjoint method, right? The adjoint problem, remember, they're always linear. So that's why people look at this, because the dual problem typically easier to solve. So what I looked at is that when I looked up the, you see that the Lagrangians over the dual problem is the minimum of the Lagrangian, and then you take the maximum. So max min problem, then you get the lambda star, which is the optimal solution of the dual problem. And there are relationship between the optimal of the primal problem, which is what we want, right? And this is the dual problem. And this is interesting because if you do substitutions, right? This is for linear problem. You see that the primal problem, which is what they do here, is a function of the dual optimal solution, which is not a surprise. And this is nothing more than ensemble. This is a common filter that you've seen before, right? It's just that how do you get this? Typically, what do you do? Woodbury formula, right? You start from the primal, you do inversion, and then you do Woodbury to get to this formula, and then you get to common gain from here. What I shown you is that is from dual view, which is essentially the same as Woodbury, right? You get the same thing, but the dual view actually nice, because dual view tell me that what I can solve an optimization, the dual optimization problem first, and then I do substitution. I can get the primal, and this is the beauty. This is the beauty. The next thing I'm gonna do is that I'm gonna randomize. It's gonna randomize the dual problems. I introduce. So let me go back here 1 second. Right, focus on the C here, which is the prior covariance. Okay, so I'm gonna introduce a random variables, which I call delta. Delta is distributed by the prior, right, on the top right corners. And then also I also randomize the data as well. So if I do this, then the D tutor is the randomized version of D. And in fact, if you take expectation of D tutor, you get D, which is the dual, right? So in other words, D tutor is actually a unbiased estimation of the D. And what I'm going to do next is I'm going to do simple Monte Carlo approximation of that expectations. Okay, so I look at a dual problem. Let me recap what I did. Dual problem with D lambda, which is the previous slide, right? And then we do a crazy thing by randomize the dual problem. And then when I randomize, then how do I estimate the expectation? I do the Monte Carlo, right? Monte Carlo here on the dual problem. So I randomize the dual problems. And then I solve the randomized problem with now lambda bar, right? And if you look at the lambda bar, you can really see very closely to ensemble common filter in a sense. But we will get them in 2 steps. Okay, so you get the lambda bar star, which is the optimal solution of the randomized problem, the randomized dual. And you already start seeing thing, right? Omega, remember that omega transpose is nothing more than the empirical approximation of the covariance, right? Okay, so and from the optimal dual approximate dual problem, I can approximate a primal problem, which is the object interest, right? What I'm going to do is I'm going to do one more randomization. If I randomize U0, right? Then I actually get to this is ensemble Kalman inversion, which is the mean, if you care about the mean, right? But if you unroll the summation here, because these are average, the second last equation average. If you unroll the sum, you remove the sums, you should look at each particle individually. This is ensemble Kalman filters. Okay. So what I have done is this. I look at the primal problems, and I look dual problem of that, and in this case the strong duality actually holds. And then when I look at a dual problem, I do a Monte Carlo randomization on dual problem and solve for the approximate dual problems. Then actually I can recover the ensemble common filter. So in other words, I know from historically ensemble common filter is not discovered that way, but in fact, you cannot do a systematic way, just randomizations, right, of expectations. Then you actually can derive it. The beauty is actually allow you to prove something different, right, than the usual thing. Now, if you look at the Monte Carlo approximation, typically you care about asymptotically when n go to infinity, number of particles going to infinity, or when the time step go to 0. Like what you ask yourself typically in practice, you only have a finite number of particles, right? How good, I have 100 particles, how good my approximation is, right? That's for non-asymptotic, right? Because that's actually a practical thing. And in the probability in high dimensions. Okay, so what I can show you here is that by looking at this from this view of optimization approach, actually I can have a different way to look at the ensemble time and field LM. It's a linear case, right? Is that the ensemble mean U bar here and the U star is the true. We can show that there, you give me any epsilon, right? But epsilon must be in that bound. And this actually depends on the forward map, the covariance operator, and the condition number of B, which related to A. Don't worry about that. So what you can see here is that one step of ensemble common filters, right, can give you a very good the mean prediction or ensemble means, right, with high probability. So there's still some probability that you fail. So that inequality is not deterministic inequality. It's a stochastic or statistical inequality. That inequality holds with high probability. What does it mean? 1 minus exponential of the order of n to epsilon squared. So n is the number of particles. So actually a few things that you can see here, right? The number of particles need to be very large in order to get good. If you said, okay, I don't want to do multiple iteration, I do one iteration, how good I am, then n need to be sufficiently large, because you see that if m is small and epsilon is the error, right? If you want small epsilon, like let's say close to 0, the expectation there going to be 1, and then you fail because the probability of success is very small, right? But another way to look at this is this: the number of particles, and I think this is interesting. I think is that if you want your ensemble mean to be epsilon with some up to constant away from the true mean, right? That you don't know, then the number of particles should be, in the order of 1 over epsilon squared to be good. At least from that, this theoretical results tell you. If you do this, then that inequality holds with high probability. Okay, so actually there's a few more results, but and actually you can show from this approach, you can also show that the ensemble time and filter can collapse very quickly. Actually, you can show it's called collapse under some conditions. You can show that is actually collapse with this approach. Okay, so what I think I start at 3:07 or so. So I have a couple of minutes for question. Okay, so again, I'm just a tourist here. I'm just going to show you some of the an optimization way of looking at ensemble time and filter. I hope that it may bring something new, or maybe completely own, because I said this is not my community, so I don't know. Maybe these are really no results, but I think it's maybe interesting. What I actually want to spend 1 minute to talk about model constrained deep learning for inverse problem. Hopefully, maybe next time I'm going to talk about that when applied to data assimilations. So what I'm going to show you here is the Navier-Stokes equations and in multiplicity form. What I have the measurement is u, right, at the final time, right? Not every time. I just measure at the final time, time to final time, and then I want to infer for the initial condition. So this is a nonlinear inverse problem, right? Okay, so what I want to do is I want to try to build a neural network actually to learn the inverse map, which is difficult, right? And I'm not going to do it in the usual way because we are engineers and scientists, right? We have a governing equations. If you just do pure data driven, it's not a good idea because the governing equation contains a huge amount of information there. And if you just do, close our eyes, do deep learning or machine learning without a model, that is a bad idea, which I'm going to show you in a second. The question is how to do it. Let me actually skip on how I do it, right? So next time I tell you. But let me show you the results. This is the initials, just one pair, right? This is initial, and then it's a final. This is the only a few points that I measure at the final time t equal to 10. And the question is, what is this one, right? This is one pair. So I have to train a network that my network not only take the data, but also take the governing equation into account, right? So if you use the naive neural network, and the beauty of this is that after you learn the neural network, is actually you learn inverse operators. What does it mean? When I have a new inverse operator, you just give me a new observation. I just evaluate neural network. I get the solution immediately without any solvents. So that's inverse operator that we learn. Okay, so if you use naive neural network, the true is in the middle. True initial condition is the middle. If you use naive neural network without any physics, then that's what you get, right? Which is far away. If you use a model constraints, that actually that we have one model constraint, the neural network, and this is T-net, T-net, which is like the 4D var problem in this community, right? And TNet again try to incorporate the physics and the data, and that one also. And when you do that, you can actually see much closer to the 40 bar if you think about try visit Tubular, which is 40 bar if you think that way, right? So it's my message is that now this possibly useful for data assimilation as well, because when the trainings can be expensive, right? Because it takes time to train. But when you train, you have the neural network that actually can evaluate the inverse operators. So when you have new observations, you thinking about each time you do the forecast and analysis, you don't have to do it anymore. You just have a new data and get the analysis immediately, right? Okay, so I think I should stop. Thank you so much.
All right, thank you, Tom. Since we're running a little bit behind, I think it's best if we postpone questions for dinner.
Sure.
And for then, according to our new plan, thank you very much. It should be Vikram that speaks now, but I believe I've seen Tim in the chat. Yeah. So Tim, if you can hear me, the plan now is that you go in place of Tam, that is at 5 o'clock, 17. Oh.
Sounds good. Thanks.
And then I guess, Vikram, could you try to share your screen? Vikram, oh yeah, thank you. You're writing in the chat. Not yet. Oh yeah, we can hear it. So we can see your desktop, and yes, now your presentation, there it went away. I'm gonna full screen, I think.
Can you see the presenter mode or the speaker mode?
We see your comments as well.
Okay, just a minute.
There, oh no.
No. Not us. It's him. It's him. It's not us because he's.
Last time we did it.
But it's because
there you go.
We have
it's good now.
On-site examples.
Looks great.
Okay. Thanks. So can you hear me, or I should raise my volume, my voice?
Sounds good, I think. So yeah, please just go ahead.
Okay, thanks. So the title of my talk is using deep learning to increase the ensemble size in an ensemble Kalman filter with the recentering technique, experiments with the Lawrence 1996 model. My name is Vikram Khade, and I work at Environment and Climate Change Canada. I'm based in Montreal, Canada. The motivation for my work is as follows. Localization is required in an EnKF because the ensemble size is far less than the model dimensionality. So capital N, big N is far less than D, which is the dimensionality of the atmospheric models. This is a very, very typical situation when working with any real model. Ensemble size is small because it is computationally expensive to run a model forecast. So the models are typically.
We're having a little trouble hearing you clearly. I believe, I don't know if it's a trouble with the connection, but maybe it could be your microphone. Could you check that it's well situated?
Can you hear me now? Better?
Yeah. Yep. Okay.
Maybe I was a bit far from the microphone. That's I'll just read out this slide once again, so please let me know if.
Yep.
Yeah. Localization is required in an EnKF because the ensemble size is far less than the model dimensionality. So capital N is far less than D, where D is the model model dimensionality. So N is typical N is typically something like hundreds, while D is typically something like millions. Ensemble size is small because it is computationally expensive to run model forecasts. As you all know, it can take quite a bit of time to run one forecast, depending on the lead time, of course. Deep learning, DL model can be trained to simulate the forecast model, and then it can be used to run multiple forecasts. Typically for real models like Environment Canada's GEM, training a deep learning model is very expensive, but running a trained model is relatively cheap. This has been shown by Wen et al. Using a different model, not ECC's GEM, but they have used a real atmospheric model and demonstrated that running a trained model is pretty fast. Increasing the ensemble size using deep learning simulated model could allow for a longer localization radius. This will improve the balance and reduce RMSE, since each observation will update variables out to longer distances. In an EnKF, as you all know, the background estimate of covariance improves as the ensemble size increases. Today, I will present some results regarding these ideas using the Lawrence 96 model, L96. Here is a brief review of the Wen et al. Paper that I mentioned. So the title of their paper is Improving Data-Driven Global Weather Prediction Using Deep Convolutional Neural Networks on a Cube Sphere. It was 2020. So they have used ERA5 as their training data, spanning this particular time frame of about 30 years. The inputs they have used for their neural network are geopotential height at 500 hectopascal, geopotential height at 1000 hectopascal, 300 to 700 hectopascal geopotential height, 2-meter temperature. And apart from that, their inputs are the insolation, mass, and topographic height. And they output these 4 fields as their forecast. So here is a summary graph of their result. Y-axis is the RMSE at 500 field. And x-axis is the forecast day going up to 14 days. The blue line is the RMSE corresponding to the DL deep learning model. And as you can see, it beats the T42, which is this curve over here. It is not able to beat the 1.9 degree resolution ECMWF T63, but it does end up beating the T42. Though this is like 14 days, in my work, I'm interested in very, very short lead time compared to the 14 days, which is, I'm interested in 6 to 12 hours, which is typical data assimilation cycle length in a operational weather forecasting model, operational data assimilation weather forecasting models. So what Wen et al. Have shown is that there's a big advantage with regards to the computational speed when it comes to model forecast. So a single GPU takes 2-3 days for the training of the deep learning model, but once it is trained, the forecasting is very, very fast. So running a trained model is very, very fast. So they have produced 1,000 model forecasts in 3 minutes, and each of this model forecast is of lead time 1 month. So here is the 14-dimensional Lawrence 1996 model equation. You might have all seen this before. So the xi's are the components, xi are the components or variables of this model. I've used d equal to 40 as the dimensionality of this model. I have set f equal to 8, which is the forcing, and I'm using an integration time step of 0.05 time units, which is approximately equivalent to 6 hours in the atmospheric model, real atmospheric models. So this model L96 has been used by many researchers as a test bed to try out new data assimilation schemes, improvements to DA techniques, etc. So there is a interpretation to each of these terms in the Lorentz 1996 model. It is a highly simplified atmospheric model. So this term can corresponds to advection, while this term corresponds to diffusion, and S is the forcing. So these components can be thought of as dynamical variables around the latitude circle, which has been explained in this particular paper by Songjong, Bag et al.
Sorry, Vikram, could I remind you, I think it worked well when you were very attentive to the microphone. Could you try to do it again?
Am I close enough now?
Yeah.
Okay. Yeah, for some reason it works for some time and then it goes away. I don't know why. Maybe I'm moving. So here is a picture of the evolution of components 0, 17, and 13 for 30 time units. And here is a picture of evolution of the first component actually, 30 time steps, first three, x1, x2, and x3. I'm defining the attractor size as the average standard deviation over all the 40. And this is just a convenient number to express the RMSC in units of this. So I'll be using this as, this is nothing very profound, but it is convenient to think of RMSC as a fraction of this number. So we all know that Lorentz 96 model is chaotic. It can be seen over here for the first component. The time series of the first component is shown in red, and the blue shows the time series of the perturbed component 1. Perturbation is 0.01 at initial time, and as you can see, the blue and red lines diverge. Computational resources used. So I used Google Collaboratory Pro, which is a public resource. I've used Keras for the deep learning. Keras is a high-level software library, which is an interface to TensorFlow deep learning library. A GPU consists of thousands of processor cores running in parallel. These are very efficient at some types of scientific calculations, which are used in machine learning and deep learning. CPU consists of a few cores. Each core has a broader instruction set than a core in a GPU. An individual GPU core is much more versatile than a GPU core. An individual CPU core is much more versatile than a GPU core. However, thousands of cores in a GPU are good at fast execution of specific tasks, such as image and video processing, deep learning, etc. All practical problems using DL are carried out using GPUs. The current work that I'm presenting is done using CPUs, but it is enough to demonstrate the principle that I am trying to demonstrate. Yeah, so here is some details of the Google Colab Pro for people who in the future and people who are not familiar with. I think most of you are. So there's a free version of Google Collaboratory. So the guarantee of resources is low, which means that it's possible that you're running some deep learning code and you are kicked off from the Collaboratory. The Google Colab Pro is paid. It's about $10 per month, and this is what I have used. So how does deep learning work? So this is a highly simplified slide, but I'll give you a very brief kind of description, and you all know most probably. So it has an input layer with some number of neurons. It has an output layer with some numbers of neurons. It has one or more so-called hidden layers. And so each connection has a weight associated with it. The weights are initialized with random values. The predictors of samples are inputted, and the deep learning DL calculates the output. The error between this output and sample target is basically calculated. So we know the correct answer from the training data set. So the predictions and the correct answers are used to compute the difference between the two. And this is called the error. This error is back propagated to update the weights. And this process is continued till all the samples are used and the error decreases to some acceptable level. So in my case, the deep learning network architecture for L96 is as follows. I have 40 input neurons corresponding to the 40 components, and I've got 40 output neurons. This picture is not entirely accurate for my architecture. I used only one hidden layer with 2000 neurons, although I don't have, and I've used sigmoid activation. So the number of weights associated, the number of weights optimized in my network is 2 multiplied by 40 multiplied by 2000. So 2000 neurons, and each of them are connected to 40. And I've got input and output. So that's where the 2 comes from. Deep learning has many moving parts, which are also hyperparameters. So here is the summary of my architecture. I've used one hidden layer. There are 2000 neurons in the hidden layer. I've used sigmoid activation function. I've used a batch size of 1000. I've used a learning rate of 0.01, and I've used RMS prop for gradient descent optimization. More advanced DL techniques like convolutional neural network and recurrent neural network have many more tunable parameters. So of course, this is summary of the best network I found by trial and error. So I'm not going through all the trial and error. So this is the end result that I got. One epoch uses all the data for training. In my case, one epoch is divided into batches of 1000 each, which means that the gradient is calculated over one batch. For L96, I generated 1,000,006 hours lead time forecast using the L96 model. This is very fast because the model is simple. With the real models, one would have to use the archive data. These million initial conditions are located in various parts of the phase space of the L96 model. This data can be thought of as pairs, predictors and predictant. The predictor is the initial condition, and the predictant, which is a target, which is forecast. So I have got 1 million samples. I use this data to train the deep learning network. So 70% of the data are used for training. The remaining 30% are used for validation, which is also called testing. And after I obtain the trained model, I store that trained model, which is just equivalent to storing the optimized weights, basically. So here is the picture that is often shown, which shows the training and testing. So on the y-axis, we have the loss, and on the x-axis, we have the epoch. So one epoch uses all the whole data set for optimizing the weights. And superimposed on the training loss curve is the validation loss curve. It's very important to make sure that these are comparable, because if the training loss is very low and the testing is high, then it means that there's overfitting. So I made sure that they're comparable. So we end up with a small non-zero simulation error. So in theory, I think it's impossible to get zero simulation error. You can always decrease it by increasing the amount of data and increasing the number of neurons. So question is, how small or large is this error? And as I said, after training, I save this model. Now to find out how large is the simulation error, I launched forecast from 200 different locations in the phase space. I used the deep learning simulated model to launch forecast from the same locations, and I calculate the error between the forecast pairs. Here is the histogram of the errors, and expressed of the RMSC, expressed as percentage of attractor size, which I mentioned earlier to be 3.4 model. So it is the simulation error RMSC is about 2% of the attractor size. The L96 model is quite low-dimensional compared to real atmospheric models. The forecast using numerical integration of L96 equation is fast. Even so, the DL model is faster by a factor of 3 in executing the forecast compared to the numerical integration of the L96 equations. As shown by Wen et al., this factor could be orders of magnitude for real models. The aim of this presentation is to demonstrate the principle of using DL to increase the ensemble size, increase the size of the ensemble in an EnKF. So we are all familiar with this diagram, which is a typical setup. So I've used Aussie. So observations are drawn from the truth trajectory. I've used the perturbed obs EnKF. I'm observing every other component. So m equal to 20. Remember that the dimensionality is 40. So I'm observing every other component. So m equal to 20. H is identity. R, which is the observation error, is set to 1% of the attractor size. Again, remember, it's just a convenient, attractor size is a convenient convenient factor to normalize the RMSE. I did experiments with 1000 DA cycles with assimilation every 6 hours. So remember that 6 hours in the atmosphere is like 0.05 units in L96. I've used box localization. Now, firstly, I do typical EnKF data assimilation experiment with n equal to 40, which is the ensemble size, and I determine the optimal localization radius to be 8 units, which is in units of the components. I do also experiments with n equal to 20 and determine the optimal localization radius to be 5 in the units of components. So here is the experiment with 2 different sizes of the ensemble, n equal to 20, RMS is 0.37, n equal to 40, RMS is equal to 0.31. X-axis shows the DA cycles, and this black curve is the observation RMSE, which is 1.0. So far I have not shown anything new. This is basically a typical EnKF experiment with n equal to 20, n equal to 40. So now I'll talk about the augmentation of these with deep learning. So first what I tried was I used deep learning, the trained deep learning model to generate all the 40 forecasts. Similarly, with another experiment, I used the deep learning model to generate all the 20, and the RMSE basically diverges. So purely deep learning ensemble does not work. So the DL simulation error is too large. So next what I do is I mix deep learning and model ensemble members. By model ensemble members, I mean basically ensemble members that are generated as a forecast coming from the numerical integration of the L96 model. So I use an ensemble size of N40, which is a mixed ensemble, which means that it consists of 20 ensemble members, NMD, denoted by NMD coming from the model integration, and NDL equal to 20 coming from the deep learning. So, but again, I find that the RMSE of this ensemble diverges as the DA experiment proceeds. This is again because of the DL simulation error. Though NMD equal to 20 ensemble members are perfect, each of the NDL equal to 20 members have a simulation error. So I solved this problem after much thought by recentering. So what I did was at the mean of the trial model ensemble is calculated, the NMD equal to 20 ensemble, and then the DL members are recentered on this mean. This recentering has the effect of correcting a part of the simulation error. Then I find that the recentering prevents the RMSE from diverging, and one obtains a stable result. So here is the result. I already showed you these 2 curves, the black curve in the previous slides, the red curve, the blue curve, which is basic EnKF experiment. With n equal to 20, the RMSE is 0.37, n equal to 40, the RMSE is 0.31. The new result is this. So with this mixed ensemble, n equal to 40, this has 20 ensemble members, NDL coming from the deep learning model and 20 coming from the numerical integration of L96 equations. And we end up with the RMSE of 0.33. So the point is that it is approximating 0.31, which uses purely a model ensemble. Another way to look at this result is that we have n equal to 20 ensemble EnKF experiment with a RMSE of 0.37. So it improves on n equal to 20 because of we have additional 20 members coming from deep learning. So in the mixed ensemble, the recentering, NDL corrects the mean error. It allows the EnKF to take advantage of the additional 20 ensemble members to improve covariance estimates. Now the question arises, can we increase this NDL and see what we get? So this is what I'm showing in this picture. So I already showed you the black, red, and blue curves. I also showed you the mixed ensemble experiment, which gave us an error RMSE of 0, which is pretty close to 0.31. So I increased the NDL further. So this is about the sensitivity to the DL ensemble size. So in each of these, 20 ensemble members are coming from the model. So NMD equal to 20 in all this experiment. And I'm just increasing the NDL. So as we can see, for NDL equal to 25, we get the best result, 0.28. But then as NDL increases, the mean correction becomes less effective, hence RMSE starts increasing. So it appears that if the DL ensemble is much large than the model ensemble, then the simulation error becomes more important and the result starts degrading. So it seems that there's an optimal combination of the size of the model ensemble and the size of the deep learning ensemble. Recentering results in ensemble mean being estimated only using the model members, which is 20. The improvements in the results is due to the improved covariance estimate due to the additional ensemble members from deep learning. The RMSE decreases from 0.37 for n equal to 20, 0.28 for n equal to 45 mixed ensemble due to improved covariance estimate. If the DL simulation error is made very small, it is possible that recentering might not be necessary. In such a scenario, the DL ensemble members will improve the mean estimate of the ensemble apart from the covariance estimate. So I did this experiment for different observation error sizes, RMSE. So I showed the result for RMSE equal to 1. I did 3 more, 0.5, 2, and 4. And in all the experiments with all the observation error magnitude, I get consistent results in the sense that the mixed ensemble is approximating the pure model ensemble result. So this is what I showed earlier. 0.31, 0.33 is pretty close to 0.31. Similarly, 0.163 for error, observation error of 0.5 is pretty close to 0.155. Similarly, in the case of obs error equal to 2 and obs error equal to 4. And for all these obs errors, I always find that n equal to 45 gives the best result. 0.142 in case of obs error equal to 0.5, 0.28 as we already saw for obs error equal to 1. And these are the other 2 experiments. So for any obs error magnitude, the minimum RMSE is realized for the mixed ensemble with n equal to 45. So of course, more experimentation is required to see if there is something special about this number. I don't think so, but especially with bigger or different models, like rather than L96, I would like to use real atmospheric models to see what I get. I did not speak of the spread. So here is a brief result of the spread for the n equal to 45 experiment. Black and the purple line is showing RMSE, while this line shows the spread. So you can see the spread is under dispersive slightly. So inflation might improve the results. So the conclusion is that a chaotic dynamical model can be simulated using a DL network given enough data. The mixed ensemble with correction applied to the DL sub-ensemble the analysis RMSE of the full model ensemble. In spite of the simulation error in each ensemble member, the improved covariance estimate allows the mixed ensemble to perform well. As the size of the DL sub-ensemble increases, this advantage decreases and the RMSE increases. The minimum RMSE is realized for n equal to 45 with NDL equal to 25. Further work with L96, these results raise several questions which can be answered using the L96 model. Sensitivity of the results to localization radius as NDL is increased beyond 20. I have to use the Gaspari-Cohen instead of localization, which will give me better results. What is the sensitivity of RMSE to NDL by NMD ratio for various values of NMD? In the work today I presented, NMD is 20. What is the minimum NMD required to obtain an acceptable RMSE? Can one use only NMD equal to 5 or NMD equal to 5 and NDL equal to 35? After all, the NMD ensemble is required to correct NDL members using recentering. As an extreme case, how about NMD equal to 1? I have to look at the spreads apart from the RMSE. Does inflation improve the results? Sensitivity, this is very important. Sensitivity to the DL simulation error. The train another DL network with more training data, resulting in lower simulation error. Universal approximation theorem suggests this is possible. How do the DA results change with simulation error? The DL network can be optimized by making it deeper and slimmer. This is something that I want to try. And lastly, what is the sensitivity of these results to observing fewer components? Remember, m equal to 20 in this work. So one can imagine m equal to 10 or m equal to 5, for example. The ultimate objective is to make this work with a real atmospheric model. Using L96 model to test out these ideas, the ultimate objective is to use this technique in the operational LATKF envar system at environment Canada. Currently, LATKF uses 256 members. The goal is to increase this ensemble size using the DL technique as discussed in this presentation. ECC's operational weather model is GEM. Right forecasts of this model over the past 20 years are available. The first step is to train a DL model to simulate GEM's 6-hour 3-dimensional forecast using this archive data. I'll be using CNN, RNN deep learning architecture to simulate GEM forecast. The archived GEM data corresponds to different GEM versions. The model parameters can be made part of the predictors. So any suggestions, questions, criticisms are welcome. Thanks.
Thank you, Vikram. All right, so once again, running quite late, so I think we'll curtail the Q&A session for now, but I encourage you to engage to the extent possible in the chat publicly as well. Yeah, I feel like I should say that probably our appreciation and understanding of your talk suffered because of the sound quality. So I hope people can still engage, but the feedback might be, the amount of it might be a little diminished because of that.
Thanks.
But thank you. And then the plan is after the break that Tim speaks next.
Yes. There's an error in the schedule because I think the next talk should start at 17:15. Okay, it's not 17. So you can have a break for roughly several minutes, and please come back at 17:15.
Hey, Tim.
Hey.
Sorry, let me turn on the volume slightly. But anyways, that's good. Oh, we can hear you.
Yeah, can you? Sure, yeah. And sorry for the mix-up. I'm not quite sure how that happened. I just did a bad time conversion.
Were you actually there, or did I just not see you?
No, I just let's see. Click window. I had just moved from the other room into my office, and I just missed your email by 15 minutes.
So we can see the screen great, but we're also seeing the previews and so on. There you go.
Full screen?
Very good. I guess we can just like that, right? Yeah.
Yeah. Why don't we? Yeah. Sounds good. And you can hear me clearly? Is that?
Sorry?
Yeah.
Is the audio, does it sound good?
I can open it.
The audio quality is better than for Vikram. I wouldn't say, unfortunately, that it's good, but it's not in and out like it was.
I think
for
maybe Vikram forgot to wear a headset. That will be much better.
Perhaps that was it.
So, yeah, I can try with, the reason I ask is I'm gonna have to exit the screen here, but I can try with I'm actually using the Mac. I can try with my headphones.
I think if it doesn't work, it's already good enough. It's just right now we have the weak ambient sound
Yeah.
on the other side.
Yeah, I have already opened. No, that's 10. And I will open Ian's.
Okay. Is this sounding any better, just out of curiosity?
Maybe it's like 10% better. Yeah.
Sure.
That's your.
All right, let's.
But I wanted to show him.
Yeah, you want to share?
So we're all set.
So you see this?
Yeah, that's different because if you don't see it, you have no way to escape.
Right, but when I share, See, let me share just to
Yeah,
show.
Tim, can you stop
Yep.
sharing because Ian wants to
Stop.
try.
All right. Hey, Ian.
Yeah.
So this thing is floating up here. It's going to go away.
Yeah, it's going to
But
be
if
about this one.
anybody puts anything in the chat, it comes back, and then
Yeah.
it has that, and you can't get rid of it, right? It's sitting in front of my slides. Here's what you do: you go to more, hide floating meeting controls. Now it's gone.
Yeah.
Okay. And now you can't get it back. You hit escape. Now it's back.
Yeah, that's
Okay.
good. And you have a better control of everything. That's good.
I think it makes this. I don't know if it makes this thing go away or not. Now this thing still stays. Unfortunately, it's in the way. But at least you get rid of the thing that's up at the top.
Yeah.
Yeah.
Okay, then
Okay.
we have the speakers.
Okay, Tim, I'm gonna see you in a bit. We're gonna have a short break.
For this, this is a limit of what is going to be just include the line for this time. Yeah.
Now I mean the same thing.
I thought so in the
Gotta change.
Okay. Okay, everyone, this is the last session of today. We have the final two talks. I'm presenting Tim Smith from Cirrus NOAA about using recurrent neural network to emulate high-resolution sea surface forecasts. Yes, Tim, we can see your presentations.
Great. And can you hear me?
Yes, I can hear you.
Great, thanks. So I just want to apologize for the mix-up this morning, or this morning for me, this afternoon for all of you there. And thanks especially to Professor Tanbui for swapping places with me today. Yeah, so today I will talk about how we are working toward using recurrent neural networks for making sea surface forecasts at high resolution. And I'll go ahead and recognize my mentor, Steve Penny, who's now at SOFAR Ocean in this work, and then my fellow collaborators, Sichun, Mike, Shinyi at Cirrus NOAA, and Jason Platt and Henry Barbanel at UC San Diego. And so first I'll talk about some motivation for this work. And I think this fits nicely with Vikram's talk right before this, actually. But the main motivation for my work stems from the ever increasing desire to move toward higher and higher resolution coupled atmosphere, ocean, weather, and climate models for prediction. And essentially, over the last decade, we've seen that including an accurate three-dimensional representation of the ocean state within a coupled model can lead to improvements in prediction skill, but particularly for predicting tropical cyclone intensity, and also for predictions on subseasonal to seasonal and decadal timescales. And within this work, what we've seen is that particularly ocean models that can explicitly resolve the mesoscale eddy field can improve our prediction skill. Essentially, this can help reduce surface biases and help improve our representation of atmosphere-ocean feedbacks. And then on especially longer time integrations, this can lead to a better representation of ocean heat uptake and reduce climate model drift. And so naturally, this work motivates the desire to incorporate high resolution coupled models into forecasting systems. But of course, forecasting systems rely on data assimilation algorithms. And these data assimilation algorithms, as we all know, make the already expensive numerical model even more expensive. And so just to illustrate this, if we had an ensemble-based DA algorithm, which of course, this is the EnKF workshop, so of course that's what we're going to do. This involves running many copies of the already expensive numerical model to get our Kalman gain and the error covariance statistics within. So really, as it stands today, incorporating high resolution coupled atmosphere ocean numerical models within modern DA algorithms remains computationally prohibitive. And so my goal is really to replace one component of such a coupled model. And for now, I'm focusing on the ocean component with a machine learning based surrogate model. The idea, as Vikram mentioned earlier, is that once we have a machine learning model trained, it makes making a prediction with that machine learning model is much cheaper than the original general circulation model. And so today I will talk briefly about the machine learning methodology of choice that we're using, at least for right now. And I'll talk about how we're integrating this with data assimilation, and then talk about some of the challenges and how we are scaling up this emulation, and talk about some simulations of quasi-geostrophic turbulence and sea surface temperatures in the Gulf of Mexico. It's kind of where we're headed. Okay, so the machine learning model that we are using, or method, is broadly referred to as reservoir computing, which is it's a relatively simplified recurrent neural network structure. And I'll just kind of talk through this figure because just to give you a kind of high level idea of how this works. Essentially what we're doing is creating a pseudo dynamical system state called a reservoir state. And we do this by mapping our variable of choice, or whatever we're trying to predict, say, surface temperature, wind speed, or something like that. We take that as our inputs and we map this into the reservoir space. We use an adjacency matrix that resembles how the nodes of this reservoir space are connected. We use that to integrate the reservoir state forward in time. And then we use an output matrix to map from the reservoir state into our output target space at future time. And essentially, with reservoir computing, only these final weights are trained. And actually the input matrix and the adjacency matrix are chosen randomly. And the punchline of this is that this output matrix, finding the weights of this output matrix is a linear solve, which makes a very computationally efficient training. But more importantly, this architecture has shown good performance in forecasting for chaotic systems. And there are a couple of references here, but I will just briefly talk about our work in in emulation development with reservoir computing. And so this plot shows the valid prediction time for a host of fairly low dimensional but chaotic dynamical systems. And so all of these L's here, these are various flavors of different Lorenz models, which you may be familiar with. And then these are two chaotic electric circuits. And essentially what I'm showing here is after training, this is the prediction skill based on initializing from 100 different random samples from unseen test data. And so what I want to point out here is that the prediction skill, this is the amount of time until we reach some threshold of unacceptable error. And this time is normalized by the Lyapunov exponent. And so we are pretty satisfied to see that we're getting, on average, we're getting prediction skill that is, usually greater than 5, sometimes greater than 10 Lyapunov time units. And this is positive to us, is indicating that this is a good method to use for chaotic systems, such as turbulence in the ocean or atmospheric dynamics. And so if you're interested in this, there are more details. This is one figure from a paper by Jason Platt, who's at UC San Diego. He's actually defending his thesis tomorrow. And you can find a preprint of work that he was leading, which is in review at Neural Networks, which basically goes through some of the important aspects of reservoir computing for forecasting chaotic systems. But ultimately, we're interested in integrating these machine learning models with data assimilation. And ultimately, the idea is that we want to replace the numerical model with reservoir computing-based surrogates, and then we want to perturb those surrogate models to get an ensemble-based forecast. And so one question that we had when we were formulating this is essentially, do these reservoir computing surrogate models give us an accurate representation of error growth in the system? Essentially, to give us the accurate error covariance matrices that we would need for data assimilation. And so to test this out, we integrated this with a wide variety of different data assimilation schemes. I'll just talk about my contribution to this work. So I integrated reservoir computing with the local ensemble transform Kalman filter. If you're unfamiliar with this particular flavor of the EnKF, it's essentially I think it lends itself to high dimensional problems and can scale well to high dimensions. And so I applied this to the 40-dimensional Lorentz 96 system, which is not high dimensional if you compare this to the a general circulation model of the atmosphere or ocean, but it was actually enough to start to run into some of the issues that we would later see. Okay, so the first thing I want to show in our results here are, this shows the time evolution of three nodes of the first three nodes of the 40-dimensional system. And you can see in blue is the evolution of the true dynamics. And in green, this shows the ensemble mean, where again, this ensemble is generated from, in this case, this is from 30 reservoir computing surrogates. And after starting with some fairly, not so great initial conditions, eventually after ingesting some sparse and noisy observations, we lock onto the truth pretty well. And so this plot just shows what's going on more fully. This isn't showing for all nodes of the system, the evolution of error over time. And I think this bottom plot kind of hits home the what we were trying to see. And so this bottom plot shows in blue error averaged over the 15 observed nodes of the system, and in green over the 25 unobserved nodes of the system. And what we can see is that after a short period, the two curves look quite similar and the error is quite low. And empirically, we were quite happy with this, because empirically this is essentially showing us that we are getting accurate enough error covariance estimates to spread information from the observed region of the system to the unobserved regions of the system. And so if you are interested in more of the details and looking at the different data assimilation schemes that we integrated with, this is just one part of a paper that was led by Steve Penny, which was recently published in James, and you can find at this link here. Okay, so next I'd like to talk about how we're scaling up our emulation framework. And first off, I'll talk about how we're making predictions of a surface quasi-geostrophic turbulence model. This is essentially an idealized geophysical fluid dynamical turbulence. And there's a Python package that we're essentially using here. And yeah, essentially this simulates the evolution of potential temperature under idealized turbulence. And so this plot, I'll just walk you through it. This is giving you a taste of our prediction here. The top row here shows the evolution of our truth, excuse me, which is the from this underlying surface QG model, from the dynamical model, which we're trying to emulate. And the bottom shows the evolution of our machine learning based surrogate. And here I'm showing the difference between each time slice and the initial conditions, just to highlight what's changing, what's evolving in the system. And so we can see, just I'll be a bit more quantitative about this in a minute, but predictions aren't necessarily perfect, but we can see, for instance, this dipole feature. There's some features that are broadly being captured by the emulator, even if they're, say, not exactly in the exact right position or at the right amplitude. At the end of the day, in terms of prediction skill, we are doing a bit better than persistence, and it can seem a bit sobering to be comparing to persistence, but just to give this a little bit of context, I'll compare this result to this figure from a paper by Niraj Agarwal. This was published in James last year, and where they did a very comprehensive study looking at many different data-driven algorithms and looking at their ability to make predictions of quasi-geostrophic dynamics. And the curve here that I want to point you to, hopefully you can see it, is this yellow curve. This is the scale of an LSTM. This is a very popular recurrent neural network structure or architecture. And the point of what I'm showing here is that this is sitting quite a bit above the persistence line. And of course, we have to take the comparison with a grain of salt because the experimental design is a bit different between our setup and theirs, but essentially it's just we feel like we're kind of moving in the right direction, at least able to beat persistence with this architecture alone. And so with this idealized model, there's been a number of questions that we've been looking into kind of before working with, say, real data from either reanalysis or a full-blown general circulation model. And just to give you a sense of that, one question we were looking into is essentially how much training data do we need? And so this plot shows, once again, the valid prediction time, the amount of time that we get a reasonable forecast, considering some threshold of unacceptable error on an unseen test data set. And what we can see here is that going from, say, 1 year of training data to 10, we get a massive improvement, but moving beyond, say, 10, 20 years to 50 years, there's we see that there's diminishing returns in using more and more training data. And the reason that I wanted to show this is essentially that there's a lot of interest in using data sets that are already out there from climate models, say from reanalysis like ERA5 or and these usually span, say, on the order of 10, 20, maybe 30 years. And so if we can expect the results from the QG model to translate, then this is at least giving us an indication that these might be good sources of data, or at least in terms of how much data we have. Okay, so lastly, I'll talk about how we are using this to work toward making data-driven predictions of sea surface temperatures in the Gulf of Mexico. And so ultimately, the motivation for this work is to eventually contribute to the hurricane forecasting system. And I've made a big deal about making high resolution forecasts. And you can imagine that for this application, this is particularly important in order to resolve the dynamics that are important for tropical cyclones. So for this, we are using the HICOM and Navy Gulf of Mexico reanalysis for training and testing. And with this data set, we have 20 years of data at 1/25th quite high resolution. So here, this is showing a blown up view of one of our machine learning based predictions. This top line shows the evolution of the true system, which we're taking this reanalysis to be the truth. And then the bottom line shows our reservoir computing based prediction. And so what we can see is that we're at least capturing the large scale motion decently well. But you can see, especially when we take this out to 36 hours, that the prediction starts to get a bit blurry and kind of overly diffuse. And so just to highlight that a bit more, you can see really that we're not preserving these sharp, any of the sharp gradients or SST fronts. And this is a real challenge essentially that we're facing at the moment. We can essentially capture the large scales, but these the frontal features, which of course we want to capture at high resolution, for these resolving the atmosphere ocean feedbacks. And so just to quantify this in a different way, we're actually seeing something similar also in the quasi-geostrophic model, but it's once again a nice test bed where we can easily quantify things. And so this is showing the kinetic energy spectrum. And so if we just focus on this left plot, this is showing the kinetic energy spectrum from the truth, which is again from the original numerical model. This gray line indicates the -5/3 slope, the different colors here resemble different timestamps for the truth, where we are evolving from our initial condition in purple to final time at yellow, in the yellow color. You can see the truth that while there's some change in the different scales, it's largely maintaining the same spectrum, broadly speaking. And then our prediction, we can see that once again we're relatively maintaining the larger scales, but then we get a decay in the spectrum in the higher frequency or the sharper features of the system. And so really this is kind of this is the outlook, and what we're looking into now is essentially how to capture some of the sharper features, these higher frequency modes, and essentially we want to bake this into the architecture of the neural network. Okay, and with that, I will go ahead and wrap up with the summary. I showed how we have been integrating this with data assimilation with the LETKF. Broadly speaking, we're capturing the larger scale features, but and we're looking toward how we can avoid overly diffuse predictions. And yeah, with that, thanks for your attention, and look for any questions if there's time.
Thank you very much, Tim. Do we have questions for Tim? One from Francesco.
Hello, Tim. Thank you for the presentation. First of all, I have a question about automatic differentiation for recurrent neural networks, because I'm not really familiar. Is it as easy as radar structures can be used for other approaches than particle-based methods?
Sorry, so I don't think I fully captured that. So you're asking about automatic differentiation and how this can be used in recurrent neural networks, is that correct?
Yeah, like how easily can be computed essentially the gradient?
Yeah, so the gradient, like with respect to the weights of the network, it's actually one reason that we like reservoir computing, is that basically because we are randomly initializing a lot of the internal weights, we actually don't have to do any differentiation or backpropagation because these are essentially randomly chosen. And so, as I mentioned, this just becomes a very simple, AX equals B, a linear solve to get the weights to this matrix. Otherwise, for more complicated, say LSTMs and recurrent neural networks like that, yeah, you would have to, I mean, I know there are at least Python packages out there like JAX, which will do automatic differentiation. And I'm sure this is built into things like Keras or TensorFlow in order to tune the weights. But I think what we've seen is actually that reservoir computing, essentially because you're not training those weights, you're less susceptible to overfitting, and you actually end up getting a bit of robustness from using these random weights. But is that getting at your question?
Say yes.
Oh,
Okay.
probably.
Okay. Happy to talk more later too, and on Slack. Alrighty.
Question from Laurent.
Yeah, I think Laurent Berthelot here. I see a bit of contradiction in your outlook. You would like to keep the
Yeah, sure. Yeah. Okay.
and then you would like to also to have very sharp predictions, but then you have to pay the price for that. If you have, say, if you want to make predictions far in the future, you rather want to be diffuse, be not too a bit vague, because otherwise you have a lot of say double penalty effect. So yeah, how much you expect that you can how sharp you think you can be, or alternatively, how do you don't want to represent your say uncertainty in your forecast?
Sorry. So are you saying there's a contradiction in essentially getting a long-term forecast while still maintaining sharp features? I mean,
yes. Sharp
yeah,
feature, you get double penalty errors.
Right. So I guess what we would want to be able to resolve the sharper features essentially to get a more accurate representation of the underlying flow, so that when we use this in data assimilation, it essentially gives us a more realistic, say, perturbed version of the real system rather than kind of an overly smooth outlook. Essentially, right now we're seeing these overly diffuse predictions. It's kind of I wouldn't trust it within a data essentially to give us the right representation of error growth. And we don't necessarily
I would follow on this. I give a comment on the preservation of the small scale sharp gradients. Maybe it's because the model doesn't have the resolution enough to preserve them. Because basically the prediction is this diffusive process. And I would suggest maybe if you take a look at, try to preserve these sharp features by just filter them out and then put them back in after you have processed the larger scale. And sort of like a multi-grid or multi-resolution representation of the model state. So we still have 2 more minutes for additional thoughts, questions. Igor has some.
One question: when you compare a very nice topic. My question was about the comparison between your forecast of machine learning and the persistence.
Yeah.
What about with DA and the dynamic prediction?
Yeah, so have we compared the performance of the reservoir computing integrated with DA with the original numerical model? Is that your question?
So Igor's question was more, do you show the comparison with persistence? Is there something similar that we did a simulation like cycling on EnKF, for example, to use as a benchmark?
Yeah, so I haven't yet integrated the larger scale predictions with data assimilation, essentially because I don't I don't really believe them as, emulators yet. And so in their ability to represent the error growth in the system. And so, yeah, so I'm really just looking at the emulation on its own. Yeah.
Okay, thanks, Tim. I think in the interest of time, we should move on, but thank you again for the talk. We have Ian Goon from CU Boulder. So let me share the screen. Which one? Here. L control. Oops, sorry.
See the full screen online.
Yeah, can you see the full screen online?
Yep. Yes, we can. Thanks.
Move this thing. Good to go? All right, thank you. I'm just going to jump right in. So if I can, here we go. So there's a two-step algorithm for doing ensemble Kalman filter. It's coded into the data assimilation research test bed, which comes out of NCAR, which is in the same town where I work. And I pulled some slides off of the Dart webpage to show how it works. So first you make an ensemble forecast. Then you push your ensemble forecast through your observation operator into observation space. Now you have an ensemble in observation space. And now we do the first step of the two steps. Everything up to now is like step 0. So step 1 is to do an analysis in observation space. Move from forecast to analysis from prior to posterior. And you can think of that in terms of increments. So for each ensemble member, you get an increment from forecast to analysis. That's step 1. Step 2, then, what you really want to update is not the observation. You want to update the state variables. So step 2 is just to do linear regression to map those increments in observation space back to increments in the state variable space. Okay. And then you keep going and cycle your data assimilation. Right. So that's a nice straightforward algorithm. It's easy to implement. One nice aspect about it is that this second step where you regress the increments in observation back to state, that's embarrassingly parallel. Every single state variable gets its own regression problem. So that's nice and fast. It's an algorithm though. So what do we know about how does it compare to theory, or what is it actually doing, right? How, are we doing anything Bayesian? In what sense are we doing data assimilation when we do this? Well, this is equivalent to a one-step ensemble Kalman filter. Equivalent in the sense of like up to round off, it gives you exactly the same answer under 2 conditions. The first being that the first step you use an EnKF. So in that in observation space, you update with a Gaussian approximation in EnKF. And then in that second step, you use a simple linear regression model and you estimate the coefficients with ordinary least squares. So under those 2 conditions, this is just a different algorithm for implementing an EnKF. And of course, we know how EnKF relates to data assimilation through Bayes' theorem and various other perspectives. But the question I want to address in this talk is that it? Is that all there is? This is just another algorithm for doing EnKF. Or, you know, if we swap out either one of these steps, do we completely lose the connection to Bayes' theorem? I mean, at that point, it's an algorithm. So you could swap out, say, the first step, don't do an EnKF there, do a particle filter or something non-Gaussian, right? The second step for regression, don't do a simple linear model, do something else, right? But if you do that, you still have an algorithm, but what is the connection to data assimilation, if any? That's what I'm going to try to address. And in so doing, hopefully open the door to ensemble data assimilation methods that are non-Gaussian, okay, that do not, they look like an EnKF, but they don't make any assumption of Gaussianity. All right, so just some background notation. So I've got 2 random variables, X and Y. they're joint PDF. I denote with brackets. I don't do P of X and Y. I just do brackets, okay? So capital is a random variable, lowercase is a value, right? The distribution that we care about is the posterior, X given a particular value of Y. That, from my perspective, ensemble data simulation is trying to generate samples from this, a distribution that has that PDF. With Bayes' theorem, you can write it as a likelihood times a prior. Okay. Hopefully this is all background for this workshop. I need to do a little bit to get to this two-step framework, though, to connect to the two-step algorithm. First, I'm going to introduce a new random variable, Z. So now I have a new joint PDF. The old joint PDF is just the marginal of the new one. You integrate out the new variable. And then the distribution of interest here, the posterior, is just the marginal of a bigger posterior. So my bigger posterior here is posterior on X and Z. And if you just marginalize out Z, you get back to what we care about. Okay. And this bigger posterior, I can expand it using Bayes' theorem too. So I have a bigger likelihood, the probability of Y given X and Z. And then I have a prior, but my prior is bigger now. It's a prior on X and Z. This doesn't get me all the way there. I have next a crucial assumption that I have to make. So in the likelihood, the assumption that I need to make is the probability of the observation given both X and Z is equal to the probability of the observation given only Z. So it's a conditional independence assumption. Just that by itself may not seem very intuitive, but so I'm going to connect. I'm going to try to illustrate by connecting to the Dart version. So you have the standard observation model. Y is h of x plus epsilon. The standard approach in Dart is just to set Z to be h of x. It's the observation, the synthetic observation, but without any error out of it. And in fact, in the Dart slides that I showed at the very beginning, that's just called Y. And in lots of the literature, that's still just called Y. But that is an abusive notation because Y involves epsilon and Z does not. And I need to, I'm fine with abusive notation normally, but I need a little more precision to make this connection. So I give it a new name. Although I made that illustration to try and help you understand what Z is, we don't need that. I don't need this observation model at all. I don't need h of x plus epsilon. And I also don't need to set Z equal to h of x. Okay? And at the end, I'll come back to that and say what it might be better to do than setting Z to h of x. All right, with that assumption, this is where I left off for my representation of the posterior. I just plug it in. We go from here to here. Okay. One more step, or sort of two more steps here. Now I address the prior on X and Z. I'm going to write that as a marginal times a conditional, right? So marginal is the distribution on Z, and then X given Z. So that's quite straightforward. And now you can see in the parenthesis here, that is a posterior distribution. That is actually, it's a likelihood times a prior. So that is the probability of Z given the observation. So plugging that back in, I now have my Bayesian posterior at the bottom. I have an integral representation for it. It's the expected value of the conditional where the expectation is taken with respect to the posterior PDF on Z. From my perspective, the goal of ensemble data assimilation is to generate samples from this. So I've got this new integral representation of my PDF. How do I generate samples from something that looks like this with an integral? Well, we all know how to do it. It's easy. And I'll try to convince you of that with an analogy. Dynamics. So I've got X at time K. I push it through my forward map, M, deterministic. I add some noise W. I get X at the next time. Right? We know how to sample from this. Let's say we wanted to sample from a distribution or from the distribution of X at time K plus 1. First, you generate an ensemble or a sample, one sample, or maybe lots of samples in an ensemble at time K. Then you apply the dynamics to each one of these samples to the ensemble members. Then you add samples of the noise. At the end of the process, you now have samples at time K plus 1. That's to make the connection to the integral representation. The PDF just at time K plus 1
you get by just integrating out the dependence at time k. So you take the full PDF at both times and you just integrate out time k, and now you've got the PDF at time k plus 1. That's what we want to sample from. That joint PDF, I write it as marginal times conditional. So now this thing that we know how to sample from, it is the integral of a conditional times a PDF. Okay. So going back to the Bayes posterior, we can sample from this thing in exactly the same way. So first you sample from this posterior on Z. That's analogous to sampling from just XK. Then you push it through dynamics, and then you're done. That's it. So step 1, sample from this distribution. Step 2, push it through this quote unquote dynamics. And now you have samples of the posterior, from the posterior. The problem with the analogy is that normally we know the dynamics, right? And in this thing, we don't know what is X given Z. Well, linear regression, simple linear regression, okay? We make a simple model. X is, so I'm going to say, just for notational sake here, that Z is scalar and X is a vector. So beta 0 and beta 1 are just vectors of regression coefficients. Eta is your residual. So here's our regression model. If you want to, you can say that it's telling you what the conditional PDF is. So the PDF of X, or the distribution of X given Z, if you assume that the residuals are normal, it means that this distribution is also normal with a mean that depends on Z and then some covariance. Right? So that's, if you want to make the connection back to a PDF, this is how we do the model. We need to estimate these vectors of regression coefficients, but we could just do it using least squares. Okay. So how does the two-step EnKF work? Not the non-Gaussian extensions, just the slides that I showed you at the very beginning. How does that work with my notation? So first you generate your prior ensemble, right? That goes back to here. This is generating your prior ensemble. In this slide, it's at time k plus 1. Oops, come on, come back. There we go. Then you generate the prior ensemble Z. Okay, in the slides here, that is where you push through the observation operator. So these guys are a prior ensemble of Z. Okay. Then you do your update in observation space. You move from prior to posterior in observation space. Okay. So now at this point, if you go back to my two-step here, we're done with step 1. Next, you need to push back through this conditional. And you do that at the bottom here. If you knew what the betas were, and if you knew what the residuals were, you would just plug in your updated Z to your model, and voila, that's like pushing it through the dynamics. Beta 0 plus beta 1 Z, that's like applying the dynamics to your sample. Then you add a sample from the residual, that's like adding noise to your model, and you're done. You have a sample from the distribution of interest. The problem is we don't know the betas and we don't know eta. So easy to find the betas. You plug in your prior ensemble to your model. You have a system of equations, 2 unknowns, beta 0, beta 1, and equations because you have n ensemble members. You just use ordinary least squares to solve for it. That gives you the betas. Next thing is a little bit tricky. What you could do is then evaluate your residuals from your regression. And then once you have the residuals, you could like try to estimate the covariance matrix of the residuals so that you could then sample. That's how we do noise in dynamics. When we add noise to the dynamics, we know what the covariance matrix is. We know how to sample the noise. That would be expensive. That's not what we do. What we actually do is say, well, I need exactly n samples of residuals. And when I plug in my prior ensemble, I have exactly n samples of residuals. So why go to all the effort of estimating a distribution and then sampling? Just use these samples from the residual. Okay, so this is your update step. It doesn't look like what's talked about in Jeff Anderson's 2003 paper, where he came up with that approach. In that approach, you just regress the increments. So increments in observation space going to increments in state space. If you just subtract the equations from the prior and the posterior here, you get exactly this expression for how the increments in observation space go back to the increments in state space. Okay, but when I derived that expression, I never had to assume Gaussianity at all, which means that you can do lots of stuff. You can extend this algorithm. And because of the analysis that I just did, you know how it still connects to base. So people had talked a little bit about doing extensions to the algorithm, but the connection between those extension and Bayes' theorem and the posterior, I think, was not clear before this. So in the first step, usually that's low dimensional. Maybe you assimilate your observations one at a time because their errors are independent, or maybe in batches or something like that. So the observation space update is lower dimensional, which means that you can use non-Gaussian approaches that would be prohibitive for the full problem. So you can use a particle filter on a one-dimensional problem, no problem. You could use Gaussian mixture methods. So Jeff Anderson has a rank histogram filter, which is a non-parametric way. Craig Bishop developed gamma inverse gamma Gaussian for the first step of this two-step process, which is a parametric approach. There's lots of stuff that you could do here. The second step, people haven't done this so much, but I'm basically just saying, like, how do you do regression here? So there's nothing new here. I'm just saying you can do regression for the second step. All right, so you could do a general linear model. You have your residual, you have your unknown coefficients, and now your phi sub j's are basis functions. So in the simple model, phi sub 1 is a constant and phi sub 2 is the identity. Right? And then if you go to monomials, you're doing polynomials. Right? You can do radial basis functions, you can do splines, you can do whatever basis functions you want. Right? Polynomials don't extrapolate well, not a good idea. But you can do whatever you want there. That may not, for example, respect bounds on your state variables. So let's say you have a state variable that's a concentration or a mass or something, and you try to do regression with this, you're apt to generate a negative mass. It's hard to avoid that with this kind of model. No problem, you do a generalized linear model. This is like literally the Wikipedia page on regression. Okay? You just transform your data and then do a general linear model for your transformed data. Jeff Anderson's rank regression approach from 2019 is an example of this. So you transform the data in both your state vector and your observation space to quantiles. So now they're both between 0 and 1, and then you do a simple linear model estimated with ordinary least squares in quantile space. Okay, so that's an example of generalized modeling approach. You could go fully nonlinear. So the nice thing about the reason these are both called linear is because the unknown parameters appear linearly. So as a function of z, it's nonlinear, but the unknown parameters appear linearly. So if you fit it with least squares, linear least squares problem, super easy to do. Right? If you want to go nonlinear, where the parameters appear nonlinearly, you can. You could say, like, I'm going to do neural networks for both G and F, both sides of this thing. Maybe that buys you some expressivity or something. The difficulty is that with that, you would then have to train a neural network for every observation state vector variable pair. And you would have to do that at every assimilation cycle, starting from scratch, because these things are not the same maps from one time to the next. Right? So that would be expensive. If you assume that your etas, your residuals are Gaussian, then you're saying that the conditional x given z, x given z, sorry, European, is conditionally Gaussian, which may sound like, oh, it's Gaussian, but you can go a long way to being non-Gaussian with a conditionally Gaussian model. This one, the generalized model, is not. It says that g of x given z is Gaussian, so x given z is not Gaussian anymore. But if you want to maybe estimate your regression coefficients using not ordinary least squares, maybe you want to do robust statistics, you use a Huber loss, or you throw out outliers or something like this, what you're doing there is you're essentially assuming a non-Gaussian distribution for eta. Right, so maybe your distribution for eta has a Gaussian core and exponential tails or something, and now you're doing robust statistics, you're throwing away outliers, you're getting a better estimate of your unknown coefficients. So, short story, there is a lot that you can do here to generalize this algorithm to fully non-Gaussian distributions, and at the end of the day, it looks exactly like a two-step EnKF. So you don't have to retool things and go to like some kind of particle flow or something like that, which is great. But algorithmically, this is very similar to an EnKF. All right, I want to show a few results. So I did Lorentz 96, 40 variables, standard setup, 0.05 model time units. I observed all the variables, 3 different observation models. I'm not going to talk about linear. It basically just shows that the code is working. The nonlinear ones, you can see it's not y is h of x plus epsilon. I am not using the standard observation model, and that is not a problem. Okay. All I need is to be able to do an update for z given y. Okay. The logit normal ones, the observations themselves fall between 0 and 1. So for any value of the state variable, you always get an observation between 0 and 1. For the log normal case, for any value of x, you get a positive value of y, but I have thrown this absolute value in here, so you end up getting a bimodal likelihood. Just quickly, I'll mention I do inflation and I do localization. It's an easy problem, so just do an exhaustive search and find the best parameters for every test that I run. Before I show the results, I want to come back to what I said about setting z equal to h of x. So that's kind of the standard approach. I don't have any h of x's here, but what you could do is you could say, I'm going to take a log transform of this, and now my observation model is h of x plus epsilon. Log of y is h of x plus epsilon. So just transform the obs, right? H of x is this absolute value though. And then if you set z equal to h of x, fine. But when you go back to do that second step and you try to do regression, you have to put a regression through a distribution that looks like this. Okay. This is basically just an absolute value plot turned on its side with noise. Yeah. And regression does not work for things like this. This is multi-valued. You don't want to do this. Okay. So the standard approach is not going to work well here. And it's not a problem. I just set z equal to x. What that does is it pushes the nonlinearity and the non-Gaussianity into the first step. But guess what? I can handle nonlinearity and non-Gaussianity in the first step. It's one-dimensional. It's not a problem. Okay. And then in the second step, all I have to do is regress increments from one state variable onto increments in the other state variables. And I don't get any of this multi-value problems. So quickly, I have no idea how much time I have left, but quickly some results. This is analysis for mean squared error as a function of ensemble size for a variety of methods. Basically, all the methods are two-step, but the ones up here are basically EnKFs. So the blue one is just a two-step EnKF. And the yellow and red ones are two-step EnKF with Gaussian anamorphosis transforms. I can talk about that later. I don't have time now, but it's basically another way of trying to relax the Gaussian approximation. Oh, okay, I'm doing pretty well, thanks. The ones down at the bottom are also two-step, but the first step is a non-parametric Bayesian update that should be convergent. RHF is Jeff Anderson's rank histogram filter. It should basically work for anything that doesn't have a delta distribution in it. Any continuous function, it's not parametric, and your limit of large ensemble size, this thing should converge. The IRHF is something I developed. It looks like Jeff Anderson's rank histogram filter, but I changed some of the approximations that I felt were weird and came up with something that ends up working better for small ensemble sizes. Okay, so I'm doing way better with this two-step version. Since I have the time, I'll mention that for the second step, all I did was simple linear regression because the problem I'm dealing with did not call for anything more advanced. Okay, the regression scatter plots for the second step were all just nice and Gaussian and linear. So no reason to go any more advanced than that for this problem. Okay, for the log normal problem, which was the one that had the absolute value, the bimodal likelihood, the EnKF was terrible. It was just completely off of the map here. So most of the time it would just blow up. And if you tweaked the observation and localization appropriately, it would not blow up. It would just be completely diverged, right? It would completely ignore the observations. And so the RMSE is just off the clock here. In this case, the Gaussian anamorphosis does help. It buys you something. This is just two different versions of Gaussian anamorphosis. So it helps you not blow up, and it helps you actually get close to the right answer. But once again, these non-parametric two-step rank histogram, improved rank histogram do far better. So I think it's correct, if I recall correctly, in both of these plots, the two-step non-parametric approaches have a better root mean squared error at 20 ensemble members than the other methods have at 200 ensemble members. And you don't expect the other methods to converge you don't expect them to converge to the same performance in the limit of large ensemble sizes, because this is not a problem of sampling error. It's a problem of non-Gaussianity. Right? And the EnKF methods, they do not handle the non-Gaussianity correctly. So the two-step does. All right, and I think I'm done early now. So thank you for your time.
Very down to basics and very interesting. Any questions for you? Yes.
So thank you for your talk. It was really interesting. If you can go back to the slide with at the beginning with X in the ops, you're saying that. Yes, exactly. So that you're trying to fit the posterior in a way, X given Y. So how does the choice of Z is modifying the form of the PDF posterior?
So I'm not changing the posterior at all. You have exactly the same posterior as long as you choose a Z that has this property. It doesn't matter. There's multiple choices that you could make that would have this property. You could choose Z equal H of X or choose Z equal X. It doesn't matter how you choose it. As long as it has this property, you have the same posterior here. The difference is that in the second step, depending on how you choose Z, the regression that you have to do might be harder or easier. It might be more or less accurate.
Hi. I didn't fully follow what you did for regression in the different examples.
So
they were all linear regressions, you said, right?
Like here?
No, in the examples.
Oh, yes. Yes. So my variable Z is X. So I just need a regression from one state variable in Lorentz 96 to the other state variables in Lorentz 96. And those regression problems for this problem ended up being really, really simple, and just saying X equals beta 0 plus beta 1 Z plus residual, that was good enough. I actually did polynomial because it's easy, and it was worse because when you try to extrapolate from a polynomial, it does a bad job. But anyways, I just did simple linear models for this example, and it worked quite well.
And you have said this two-step approach is quite general, and since it's sequential in the observation space, then you can do whatever you like. For example, particle filter. I would just like to remark, I think that you will still run into the first dimensionality, even though you're just doing a one-dimensional problem, just because you're doing maybe 10,000 of them. There's still no magic fill instant, despite doing regression back.
Right. Yeah, I didn't use the particle filter because I actually think it's not a good. I think that the non-parametric transformation approach here is a better way of doing it. And certainly it's possible that you can, you know, through some sampling error problem, you could not have a good result. But if you are doing sequential, and let me comment also that the derivation here, I never have to assume that Z is a scalar either, right? It's just that if Z is not a scalar, then the first step of the process might be more expensive. Right? But in the case where Z is a scalar, I really think there is not a cursive dimensionality for the first step. You're just doing a one-dimensional Bayesian problem. And
yeah, it's just that they accumulate onto the weights still accumulate on X, right, on the particles.
yeah, maybe we can talk offline. I mean, the sampling errors for this one, for the two-step stuff, are much better. You know, I do an excellent job here with this stuff at 20 ensemble members, better than you get with 200. So I think sampling errors are not as much of a problem for these methods.
I don't think Anderson's ever showed such good results with just filter.
No, I don't think so.
You found a better case, huh?
Yeah. Well, part of the reason, so he is not choosing Z equals X. He's choosing Z equals H of X. And then when you regress, if you have an absolute value, you still have to regress through this. So in the two-step algorithm that's implemented in Dart, Z is H of X. And then you have this problem.
Definitely get that with enough.
Okay, I think this is the end. I still see two questions, but we can do this offline. Okay. A final shout out to all the participants that stick to the end, especially online. I know maybe some of you are from the other part of the globe and it's really late. And thank you very much. Let's give a round of applause for all the speakers today. Although, do you have any announcements before we?
Yes, then we will start a post session. And we have some beers to cheer you guys up. This is a long day. Please just go to the bar and say that it's actually in the North Brookfield. Is that correct?
But we don't have time to use the tap. I'm sorry about that.